In the silent depths of space, a spiral galaxy drifts in splendid isolation. Its disk of stars and gas has swirled undisturbed for countless ages, tracing graceful spiral arms. But far away, another galaxy lies on a slow collision course, and neither yet senses the inevitable meeting to come. Across millions of years, gravity pulls them subtly closer, a destiny set in motion, even while everything still appears calm and unchanging. Without warning, the distant speck of light begins to grow. What was once a faint smudge on the cosmic horizon brightens as the galaxies draw near each other. Their mutual gravitational fields reach out and intermingle long before the stars actually meet. The outermost stars of each galaxy feel a new, insistent tug from across the void. Slowly, the shapes of these galaxies begin to change. Spiral arms that were once symmetrical now start to twist and stretch towards the approaching intruder. When galaxies have their first close encounter, it is like a slow dance of giants in the dark. One galaxy glides past the other in a cosmic flyby, and each one's gravity pulls on the other's stars, gas, and dust. The orderly pattern of their disks is disturbed by this gravitational caress. A spiral arm might be drawn outward, pulled by the passing partner's invisible hand. Arm might collapse inward or kink as the galaxy responds to the shifting gravitational forces. Through this gentle but inexorable tug-of-war, the galaxies become distorted, their starry disks responding like water stirred by a passing ship. In the wake of this near passage, something remarkable appears. Luminous trails of stars and gas furl into space. These are tidal tails, long, delicate streamers torn from the galaxy's outer regions by gravitational tides. Picture a spiral galaxy sprouting an ethereal ribbon that stretches far beyond its main body, like taffy pulled into a thin strand. Along this tenuous strand, countless stars glitter, cast out into the intergalactic night. Clouds of glowing nebulae are drawn along as well, spread like a gauzy bridge between the separating galaxies. Each tail can extend for tens or even hundreds of thousands of light years, a spectacular ribbon of starlight, marking where gravity has pried a galaxy apart. Astronomers call these structural because they resemble the tides of an ocean on a scale of galaxies. Just as the sea raises bulges of water on Earth, the gravity of one galaxy raises a tide of stars in another. The galaxy seems to spill some of its contents into space, pulled into those elongated tails. Cosmic tides reach their peak as the galaxies make their closest approach. Then, as the galaxies begin to separate again, the drawn-out material lags behind, forming trailing and leading streams, tidal tails that slowly. Often there are two such tails, streaming out in opposite directions from the site of the encounter. One may trail behind a galaxy as it moves onward, and another may lead ahead, flung forward into space. In some encounters, one tail reaches toward the companion galaxy itself, forming a luminous bridge directly linking the two. It is as if the galaxies are momentarily connected by a glowing umbilical cord of stars, a cosmic pathway forged by their mutual gravity. Through this stellar bridge, it flows from one galaxy toward the other, binding the pair in a brief, shining link across tens of thousands of light years. These tidal bridges and tails stir the very structure of the galaxies. The flyby sends ripples through each galactic disk, jostling stars from their familiar orbits. Waves of higher density roll through, compressing gas clouds and triggering clusters of new stars to form. Even in the stretched out tails and remote bridges, new stars can be born. Bright blue star clusters punctuate the tidal streams, sparkling like cosmic fireflies, scattered along a wispy trail. Occasionally, the clumps in these streams may grow into tiny new galaxies themselves, so-called tidal dwarf galaxies, formed from the cast-off debris of the encounter. From afar, astronomers have indeed of such celestial sculptures, frozen in mid-interaction. The antennae galaxies, for example, locked in each other's embrace, and spectacular twin tails that span hundreds of thousands, curving outward like the antenna-like appendages of some cosmic creature. In another corner of the majestic whirlpool galaxy extends a faint bridge of light to its companion, a visible stars drawn out by their gravitational dance. These vivid examples reveal a strange mix of elegance and violence at first contact. Galaxies in the act of transformation, their original forms stretched and deformed by the force of mutual attraction. As the galaxies drift apart after their flyby, they carry permanent marks of the encounter. Their flat disks may now be warped or tilted, as though twisted by an invisible hand. The newly formed tidal tails arc gracefully into space, and will remain for a time as reminders of the cosmic encounter, slowly dispersing over eons. Some of the drawn-out gas and stars may eventually rain back down onto the galaxies, perhaps to resettle into new orbits or future generations of stars. Some material may escape entirely, flung beyond the galaxies into the intergalactic void as solitary roving stars. Not every close encounter ends in a complete merger. Sometimes the galaxies pass by each other only once, then continue on separate trajectories, never to meet again. Even a single flyby, however, is enough to leave both galaxies forever changed. A spiral may be set ablaze with new star formation, its core rattled and its pattern of arms altered by the gravitational rapture. A smaller galaxy might be nearly stripped of its gas by a larger one, left exhausted in the aftermath. Both emerge transformed, bearing the subtle scars and splendid plumes of their near collision. In the grand scheme of cosmic evolution, these first are gentle preludes to more violent unions. They are the initial flirtations of galaxies that merge. If gravity binds them strongly, their paths will cross again and again. Each subsequent encounter draws them into a tighter orbit, slowly draining away orbital energy and bringing them ever closer. Over hundreds of millions of years, what began as a glancing pass can turn into an inevitable embrace. Two galaxies, entwined by mutual gravity, will eventually spiral inward toward a common center. The stage is set for a true collision, one that will meld them into a single entity. When that moment arrives, the outcome of the merger will depend on a crucial factor: the balance of their masses, the relative size of each partner in this cosmic dance. Galactic encounters that begin as a gentle dance can crescendo into a full collision. When two galaxies finally merge, their stars and gas clouds intermingle in a chaotic embrace. The once separate disks are now entangled, and the graceful spiral patterns are erased amid the tumult. Stars are sent ricocheting onto new paths under the combined gravity, as if flung by a cosmic slingshot. Yet remarkably, despite the appearance of a collision, individual stars almost never hit one another directly. The vast gulfs between them see to that. Instead, the galaxy's overall structures collide and distort, their stars changing course en masse like flocks of birds suddenly swerving. As the cores of the galaxies draw together, they begin to orbit a common center, looping around each other. Each pass drains more energy from their motions, like two dancers growing weary as they tighten their hold. The galaxies swing through each other, trailing more stars and gas with her. Eventually, their separate identities blur. What was once two distinct star cities becomes an extended cloud of stars, gas, and dark matter, all bound in a single gravitational field. The final coalescence comes slowly. The central regions merge into one, and the tidal debris falls back or drifts away. In the aftermath, one new galaxy emerges, where once there were two. The fate of that new galaxy depends largely on the balance of masses between the original pair. When two giants of comparable size collide, a major merger, neither yields easily. Both galactic disks are heavily damaged, their rotational order disrupted beyond repair. In the violent commotion, many stars trade the orderly rotation of a disk, wild, plunging orbits that carry them far above and below any plane. The result, stellar swarm that is more spherical or ellipsoidal in shape rather than a flat disk. In effect, the merger has created a vast stellar cloud, a spheroidal galaxy where once there might have been two spirals. These stars now move, like bees swarming around a new hive, no longer confined to the neat spiral traffic lanes they once followed. Such a merger between equals often gives birth to an elliptical galaxy, an amorphous, rounded system of stars lacking the elegant arms of a spiral. The encounter stirs up and randomizes the motions of millions of suns. Any cold disk of gas that existed is largely shaken and shocked. Much of it may fall inward or be expelled. With the gas consumed or scattered, new star formation eventually slows, and the merged galaxy settles into a more quiescent state. In its core lies a dense concentration of stars, likely accompanied by the merged supermassive black holes of the original galaxies deep in the center. The outer regions bear faint traces of the carnage. Shells, or long, faint streams of stars arching outwards, markers of the violent union. Over billions of years, these features will fade, and the system will resemble a single, giant elliptical galaxy, slowly aging and reddening as its star formation wanes. But not every galactic collision is a clash of equals. Often, a large galaxy will merge with a much smaller companion, a minor merger. In these encounters, the massive galaxy acts as a cosmic predator, and the smaller galaxy as its prey. The smaller system is strongly affected. Its stars and gas torn from their original home and absorbed into the larger galaxy's halo or disk. The big galaxy, by contrast, is disturbed but not destroyed. It may wobble and grow a new ripple or warp, but its overall structure survives the ordeal. One might picture it as a giant ocean liner ploughing through a small wave, altered slightly by the splash, but continuing on its course. In a minor merger, the primary galaxy's disk can endure and even rebuild itself after the interaction. During the merger, the smaller galaxy's material is strewn through the larger one. Some of the infalling gas rains down onto the larger galaxy's disk, sparking new stars and thickening the fresh material. The influx of stars from the smaller galaxy may puff up the larger galaxy's thin disk, creating a thicker, more spread out stellar distribution. These shaken stars gradually settle into new orbits. The spiral structure that might have been temporarily distorted can reform, especially if there is still abundant gas to reshape into new spiral arms. In this way, a disk destroyed in the heat of merger can, given enough time and remaining gas, be reborn. The remnants of the smaller galaxy typically become part of the larger galaxy's halo or central bulge. Many of the smaller galaxy's stars are flung onto wide, looping orbits around the outskirts of the big galaxy, forming faint streams or a diffuse halo of ancient stars. Some of its stars sink into the larger galaxy's core, adding to the bulge at the center. The chemistry and ages of these stars can betray their foreign origin. They may have different compositions or motions, clues that they were not born in the larger galaxy's original disk. In a sense, the large galaxy has cannibalized its companion, digesting its stars and gas. Mass matters. A merger between equally matched spirals to destroy the delicate disk structures, whereas a merger between an uneven pair keeps the main disk intact or able to reform. This is why many large spiral galaxies can continue to exist, despite having swallowed numerous smaller galaxies over their lifetimes. Each minor feeding only subtly alters the spiral, perhaps enlarging the central bulge or producing a faint ripple in the disk, but the spiral character remains. Only a truly major collision has the power to entirely reshape a spiral into an elliptical, erasing its disk completely. Over the history of the universe, galaxies have grown both by dramatic mergers of equals and by countless minor accretions. A single major merger can transform two flourishing spirals into one quiescent elliptical. In contrast, a series of minor mergers, accumulated over billions of years, can gradually build up a galaxy's mass while preserving a form. Indeed, astronomers theorize that some elliptical galaxies might have formed not in one cataclysmic event, but through the cumulation of many smaller mergers that slowly stirred their stars into a spheroid. Nature offers multiple pathways. A galaxy can be violently in one great crash, or quietly remodeled through a slow diet of tiny galaxies. In cosmic terms, the end, whether a smooth elliptical or a revitalized spiral, sets the stage for the galaxy's next chapter. A newly formed elliptical, left isolated, will shine as a rounded system full of aging stars. A spiral that endures might emerge with a new burst of life, its spiral arms replenished with fresh stars and gas. Either way, the galaxy has been altered by the encounter, its evolution redirected. The sky is filled with these merger remnants in various stages, some still sporting tidal tails or distorted shapes from a recent union, others already settled into equilibrium, as if they were always that way. Each one is a testament to the importance of mass in galactic destiny, the cosmos's lesson that in galactic mergers, size matters. Yet structural changes are only part of the story when galaxies unite. The violent gravitational dance can have another spectacular consequence, a burst of creation amid the destruction. As the galaxy's gas is jolted and compressed by the merger, it can crash toward the center or into dense clouds, sparking furious episodes of starbirth. Before the new galaxy settles into its final form, it may blaze with the light of countless young stars born from the chaos. These merger-triggered starbursts are like cosmic fireworks, brief but brilliant, lighting up the scene of the collision and transforming the galaxy's gas and dust into a glittering stellar celebration. When galaxies collide, or even brush close, it is not only their stars that are set adrift. The gravitational upheaval sends shockwaves through their vast clouds of gas. Giant molecular clouds that once drifted in stately orbits are jostled and squeezed. Streams of interstellar gas, perturbed by tidal forces, begin to lose their gentle circular paths, drawn by gravity, lowest point of the new combined gravitational field. Much of this gas flows inward. It is like a great cosmic avalanche. Gas that was spread through a galaxy's disk now cascades toward the center, funneled by the distortions of the collision. As the gas piles up in the core, it becomes ever denser. Under increasing pressure, sleeping clouds of hydrogen wake as sites of furious creation. In a relatively brief span, only tens of millions of years, the galactic center can transform into a cauldron of Earth. Astronomers call this a starburst, an intense but short-lived epoch when a galaxy's star formation rate rockets upward. Where before the galaxy might have formed a few new stars a year, now hundreds or even thousands of stars ignite in the same span of time. The nucleus of the galaxy blazes with youthful light as innumerable hot blue stars come into being together. To an observer, it is as though the galaxy has caught fire in its heart. The core glows with the combined radiance of massive newborn stars, each pouring out ultraviolet light and stellar winds. So many bright stars crowding the center can make the galaxy dozens of times brighter than before. Through telescopes, such a galaxy might appear to have a brilliant, compact center, a beacon of blue-white light amid the older, yellower stars around it. This is the cosmic equivalent of a flash fire or a fireworks finale, a sudden outpouring of energy and light as new stars flood the scene. The drama does not stop at visible light. These newborn stars heat the surrounding dust, causing the galaxy's core to shine fiercely in infrared wavelengths. Buried in thick clouds, much of the starburst's brilliance is hidden to human eyes, but it emerges as thermal glow detectable to infrared telescopes. In effect, the heart of the galaxy becomes an oven, dust grains soaked in starlight, radiating warmth. Some of the most luminous galaxies in the universe, radiating prodigious energy in infrared, are starburst galaxies caught in the throes of mergers, their central star-forming firestorms so dust-enshrouded that they are barely visible in ordinary light. Within this maelstrom, distinct structures can also appear. As gas funnels inward, it may not all plunge straight into the very center. Often it rotates as it falls and gets hung up in a circular orbit, forming a ring of gas and stars around the nucleus. In many interacting galaxies, these nuclear rings shine as wreaths of intense star formation. They resemble a glowing necklace encircling the galaxy's core, studded with brilliant clusters of young stars like cosmic gemstones. Such rings form where the inflowing gas hits an inner resonance, essentially a traffic jam in the galaxy's gravitational environment, causing it a certain radius. The stalled gas in the ring then bursts into star formation, lighting up a bright ring around the calm eye of the galactic center. Seen from afar, a nuclear starburst ring is a mesmerizing sight. One can imagine looking down at a galaxy and seeing a luminous circle traced around its heart, perhaps tens of thousands of light years across, filled with blue and pink knots of new stars and glowing nebula. Each knot marks a cluster of massive stars blazing, illuminating the surrounding gas. These rings for a while, fueled by continuing inflow from the outskirts. They are like cosmic campfires burning in a ring, fueled by the steady supply of gas streaming inward from the disk. Eventually, however, the frantic pace of starbirth exhausts its fuel. Starbursts, for all their brilliance, are fleeting phases in a galaxy's life. The massive stars being born live fast, die young. Within a few million years, the most luminous among them explode as supernovae. In a starburst, supernova detonations become commonplace, each one blasting surrounding gas shockwaves. The combined fury of hundreds or thousands of supernovae creates a ferocious feedback. Like a series of powerful storms, they stir and heat the remaining gas and can drive much of it outward. In some starburst galaxies, we see the aftermath of these explosions in giant outflows of gas, great bubbles and cones of material billowing out from the galactic center. These galactic superwinds carry the signature of its violence. In the nearby starburst galaxy, M82 for instance, astronomers observe colossal red plumes of hydrogen gas streaming perpendicular to the galaxy's disk, material blown out by countless supernovae in its central region. Such outflows vent the energy of the starburst into intergalactic space, like chimneys releasing pressure from a raging fire. But as they do, they also deplete the galaxy's central reservoir of gas. Eventually, the burst of star formation can no longer sustain itself. The firestorm dies down, leaving behind a quieter galaxy. In the wake of a starburst, the galaxy carries on with a changed complexion. Regions that were once lush with cold gas become emptier and often populated by a new generation of stars. These stars, having formed in a crowd, gradually disperse through random motions, adding a flicker of youthful blue to the older stellar population. If the merger or interaction continues, more gas might yet rain in to trigger subsequent bursts, but often the most dramatic episode is over. The galaxy, having blazed so brightly, now settles into a calmer phase, at least until the next disturbance. Galactic collisions and close encounters thus have a dual role. They not only morph the shapes of galaxies, but they can also rejuvenate them briefly with stellar fireworks. A spiral galaxy that might have been slowly aging can suddenly, due to an interaction, undergo a renaissance of starbirth. The result is a spectacular transformation of energy, a tempest of creation amid the chaos of destruction. Such starbursts stand out in the universe as beacons of change, marking the moments when the cosmic dance of galaxies becomes a feast of new light. Starburst rages, other processes may stir in the heart of the galaxy. As vast amounts of gas pour toward the center, not all of it goes into forming stars. Some of it may spiral all the way down into the maw of the galaxy's central black hole. Interactions can thus fuel active galactic nuclei, brilliant quasars or Seyfert nuclei, where a feeding black hole outshines the entire galaxy. But whether it manifests as a burst of star formation or a quasar's glare, the inflow of gas during galactic encounters ensures that the center stage of the galaxy becomes a scene of extraordinary activity. In the cosmic ballet of colliding galaxies, this is the dramatic crescendo, a short-lived blaze that leaves permanent imprints on the galaxy's stars and gas. Over time, the heightened activity subsides. The new stars disperse, the supernova-driven winds blow out or fall back, and any active nuclei down once its fuel is spent. What remains is a galaxy significantly changed by its encounter, perhaps with a larger central bulge due to those new stars and the stirred orbits, perhaps with available for future star formation. It has lived through a starburst firestorm and come out the other side. In the narrative of galactic evolution, these fiery eggs are pivotal chapters, temporarily reversing the aging of a galaxy and crafting brilliant new stars, even as the collision reshapes the galaxy's form. As the last embers of the starburst fade, the galaxy's evolution continues along its altered path. The interaction that triggered the outburst may still be ongoing, driving further changes in structure and motion. The next consequence of the encounter is already unfolding in how the stars move. In the subtle shifts of orbits, impossible new patterns of rotation, or layers of stellar populations. The collision has not only made new stars, it has rewritten the motions of many existing ones. In the next act, we will see how these violent unions leave lasting marks on the kinematics of galaxies, warping disks, creating counter-rotations, and puffing up their stellar distributions into new dimensions. Long after a galactic collision has passed, the visible scars may fade, but the motions of stars and gas carry a memory of the upheaval. Interactions can fundamentally rewrite a galaxy's kinematics, the patterns of movement that its stars and gas follow. Imagine gazing at a once quiet spiral galaxy after it has endured a cosmic encounter. To the eye, it might still have a disk and spiral arms. Yet, hidden in the velocities of its stars are clues that the galaxy's orderly rotation was disturbed. Some stars now orbit in unexpected ways, revealing the enduring influence of past gravitational turmoil. One striking example of kinematic transformation is the phenomenon of counter-rotation. In certain galaxies, not all components rotate in the same direction. A portion of the stars, or gas, may be moving opposite to the rest. It is as if part of the galaxy is trying to rewind time, spinning backward against the overall flow. This curious state often arises from the merger or accretion of a companion galaxy on a retrograde orbit. Picture a smaller galaxy falling into a larger one from the wrong direction, against the direction the larger galaxy's disk rotates. The smaller galaxy's stars, upon assimilation, continue to orbit in their original direction, which for the big galaxy is the reverse way. As a result, the merged galaxy ends up with two intermingled populations, one rotating one way and a second moving the opposite way. To a traveller within that galaxy, half the stars rise in the east, while the other half rise in the west, each following its own course. Astronomers detect these counter-rotating components by measuring the light of stars and gas and detecting Doppler shifts on opposite sides that reveal contrary motion. What they have found is astonishing. For instance, one galaxy has its gas orbiting opposite its stars. Another galaxy hosts two stellar disks superposed, one rotates and the other counterclockwise, precisely the situation observed in the galaxy NGC 4550, where two equal-mass stellar disks cohabit but spin opposite ways. These cosmic dance patterns are the direct imprints of past mergers. A smaller galaxy, captured on a reverse orbit, has grafted its rotation onto the larger one in reverse. Another subtle reconfiguration wrought by interactions is the warping of galactic disks. In a perfectly undisturbed spiral, stars and gas orbit in a single flat plane, like a well-aligned frisbee. But many spiral galaxies, including our own Milky Way, have outer disks that are slightly bent or twisted. The disk might bow upward on one side and downward on the other, forming a gentle S-shaped warp when viewed edge-on. Such warps can be triggered by the gravitational pull of nearby companions, or the lingering effects of an earlier encounter. When a passing galaxy tugs on the edges of a disk, it can set the orbits of the outer stars and gas precessing out of alignment, causing the whole outer region to wobble. These warps are often most noticeable in the galaxy's cold hydrogen gas layer, which extends far beyond the visible stars and is more easily flexed. In radio maps of spiral galaxies, the gas disk curls like a brimmed hat, deviating from the flat mid-plane as it reaches the outskirts. Left alone, a warp might eventually settle, but repeated encounters can keep disks perpetually flickering and bending. Our Milky Way's disk is not perfectly flat. The influence of orbiting dwarf galaxies and the surrounding halo have set it gently rippling. As a galaxy moves through the gravitational fields of its neighbours, its disk can ring like a gong struck long ago, the oscillations slowly fading, but never fully gone. Perhaps one of the most consequential kinematic imprints of minor mergers is the formation of a thick disk. Spiral galaxies often have not just a single disk of stars, but two. A thin disk, where most young stars and gas reside, and a thick disk made of older stars that extends further above and below the galactic plane. The thick disk is a clue that at some time in the past, the galaxy was dynamically heated. When a smaller galaxy merges into a larger spiral, it doesn't simply contribute stars. It also gravitationally perturbs the orbits of the pre-existing stars. Like stirring milk into coffee, the merger causes stars that once moved in an orderly thin layer to scatter to higher inclinations. In a thin disk, stars bob only slightly up and down as they orbit, keeping to a narrow plane. But the agitation of a merger can kick some stars onto orbits that climb higher above the plane or dive below it, increasing their vertical spread. Over billions of years, these perturbed stars form a diffuse, thicker disk component. The thick disk stars tend to be older and less metal-rich, suggesting they are remnants of an earlier era of mergers and chaos. After the stir of a minor merger, the remaining gas in the galaxy can settle back into a new thin disk, gradually forming new stars in a more orderly plane. Meanwhile, the older stars remain in their puffed-up, heated orbits, a permanent record of the long-ago merger. The presence of a thick disk is like finding a layer of sediment in a geological formation. It tells a story of Many galaxies bear this stratified look when studied carefully, a dense, thin disk embedded in a fainter, thicker one. Our own galaxy is no exception. The Milky Way's thick disk contains stars with distinctive chemistry, likely debris from one or several ancient mergers that churned our galactic disk and then mixed in their own stars. The thin disk that we see today, rich with young stars and neatly arranged in spiral arms, grew later from the ashes of those turbulent times. All these kinematic artifacts, counter-rotating cores, warped disks, and stellar layers, are often invisible in a casual photograph of a galaxy. To the eye, a spiral galaxy might look serene and symmetric once its tidal tails fade and its starburst sputters out. But by decoding the motions of its stars and gas, scientists reveal a hidden history written in dynamical terms. A gentle warp here, a population of stars moving oddly there, or a vertically extended distribution of old stars. Each is a signature of gravitational encounters that shaped the galaxy's past. These clues underscore that even when galactic interactions are done twisting the galaxy's visible form, they continue to echo in the motions of its constituents. It's as though the galaxy remembers the encounter in the patterns of its stars' orbits. Long after two galaxies have merged into one, the new galaxy carries within it the kinematic handwriting of that. By reading this handwriting, astronomers can reconstruct stories of cosmic meetings that happened billions of years ago. Galaxies do not evolve in isolation, and these dramatic encounters are often influenced by the larger environment. A galaxy in a sparse region of space might endure only an occasional interaction, whereas one cluster faces constant gravitational harassment. The broader environment into which a galaxy is born amplify or mitigate the kind of transformations we've been exploring. Having seen how one-on-one encounters and mergers alter galaxies internally, we now turn to the role of the environment at large. The bustling arenas of groups and clusters, where galaxies not only merge, but are also shaped by a dense cosmic community. Galaxies are not scattered uniformly in space. They congregate in various social settings, from intimate groups of a few members to enormous clusters containing hundreds or thousands. The environment a galaxy lives in plays a profound role in its fate. An isolated spiral drifting in the cosmic field might evolve slowly, undisturbed, except for the occasional small companion. But place that same galaxy in a dense cluster, and it finds itself in a crowded city of galaxies, subject to constant gravitational jostling and the pressure of a hot intracluster medium. In these bustling environs, galaxies are transformed by forces that never come into play in quieter solitude. In small groups, interactions occur at relatively low speeds. The galaxies within a group, like the members of our local group, orbit each other leisurely. This gives them ample time to tug on one another, even to merge. Many galactic mergers likely take place in such groupings, where a pair of spirals might slowly coalesce over 1 billion years. The result can be a larger spiral or an early type galaxy formed from their union. In groups, the pace of encounters is less frenetic, and individual mergers can unfold without being immediately disrupted by a third intruder. A galaxy in a group might have one major interaction at a time, with periods of respite in between. Contrast this with a rich cluster, where hundreds of galaxies swarm in a volume only a few million light-years across. Here, relative velocities are enormous. Galaxies can zip past each other at thousands of kilometers per second, too fast to readily merge upon encounter. Instead of graceful mergers, cluster galaxies suffer a more cumulative kind of assault. One phenomenon is known as galaxy harassment, a series of rapid, close encounters with multiple neighbors that, over time, can shake a galaxy to its core. Each flyby is like a sudden tug on the galaxy's stars and gas, imparting a little chaos into its structure. A single high-speed encounter might not do much more than excite some transient disturbances, but dozens of them, experienced one after another as the galaxy careens through the cluster, can gradually tear away at the galaxy's stability. A spiral galaxy entering a massive cluster may begin as a beautiful, gas-rich system with spiral arms and ongoing star formation. After a few billion years in the cluster's interior, that same galaxy might emerge unrecognizable. Harassment by many small gravitational encounters can distort its disk, knocking stars onto new orbits and erasing delicate structures like spiral arms. It's rather like a ship entering stormy seas, buffeted from all sides by waves, in this case, gravitational tides from other galaxies. The once orderly vessel can lose its rigging and shape. The main is a more featureless disk or a spheroid, something closer to a lenticular or dwarf elliptical galaxy. In fact, astronomers suspect that many of the dwarf elliptical galaxies found are former tiny spirals that have been harried into giving up their gas and structure through this ongoing barrage. Harassment, however, is only part of the story. It can contain another agent of transformation, the pervasive hot gas that fills the space between galaxies. This intracluster medium is a diffuse plasma, heated to tens of millions of degrees and visible in X-rays. When a galaxy plunges into a cluster, it encounters this medium much like a speeding car entering a thick atmosphere. The galaxy's motion through the hot gas creates a wind relative to the galaxy, and this wind can be powerful enough to strip gas right out of the galaxy's disk. This process is called ram pressure stripping, and it can rob a galaxy of the very material it needs to form new stars. Imagine a spiral galaxy falling into a cluster at high speed. Its own reservoir of cold gas, the fuel for star formation, is largely concentrated in its disk as clouds and diffuse hydrogen. As the galaxy hurtles through the intracluster plasma, pressure builds on its leading edge. The hot wind pushes against the galaxy's gas, and if the pressure exceeds the gravitational grip the galaxy has on that gas, the gas gets swept away. One by one, clouds of star-forming material are pried loose from the galaxy's disk and blown downstream, leaving behind stars, but no fuel for future star birth. To an observer, the infalling galaxy might grow a peculiar appendage, a tail of gas and newborn stars trailing behind it, glowing as the stripped gas undergoes a last burst of star formation on its way out. These are the so-called jellyfish galaxies, named for the trailing tentacles of material that extend from their disks. In the nearby Virgo cluster, for instance, we see striking examples of this phenomenon. Spirals with bright blue streams of star formation flowing behind them, Vivid proof of Ram pressure in action. Ram pressure stripping can be dramatic. In some cases, a spiral galaxy entering a cluster is almost completely gutted of its gas after a single pass through the cluster core. Where once there were swirling spiral arms rich with nebulae, now only a skeletal disk of stars remains, like the bare frame of a ship stripped of its sails. Devoid of its interstellar medium, the galaxy can no longer sustain much new star formation. Over time, the remaining stars age and grow redder, and without replacements, the galaxy begins to take on the quiescent appearance of an early type system. What was a blue, active spiral transforms into a red, gas-poor, lenticular, or faint elliptical. In effect, the cluster has quenched the galaxy's life in terms of making new stars. This quenching by environment is a key driver of the observed differences between galaxy populations, in clusters, and in the field. In the dense heart of a rich cluster, most galaxies are found to be ellipticals or lenticulars with little or no star formation. By contrast, far from the cluster in the general field, spirals and irregulars, often actively forming stars, dominate. This segregation is known as the morphology-density relation. In regions of higher galaxy density, like clusters, early type, elliptical and lenticular galaxies prevail, whereas in low-density environments, late type spiral and irregular galaxies thrive. The forces of harassment and Ram pressure help to explain this pattern. Clusters effectively process galaxies, turning many spirals into gas-stripped, smoothly featured systems. Not only do individual galaxies change under these conditions, but their interactions take on new character. In the chaotic cluster environment, true mergers are less common because of the high speeds, yet when they do occur, they can be spectacular, often involving a larger galaxy absorbing a much smaller one, captured by the cluster's gravitational well. Meanwhile, the central regions of clusters often host one or more gigantic elliptical galaxies, thought to be the product of numerous mergers and cannibalism of smaller cluster members. These giants sit like monarchs at the cluster's core, sometimes exhibiting extensive CD halos, enormous envelopes of stars that may be the accumulated debris of galaxies torn apart in the cluster. Their presence is another cluster's role as a cosmic melting pot. In group environments, galaxies can also face gas removal, and though typically less violently, a galaxy group might not have a hot intragroup medium as intense as a cluster's, but member galaxies can still gradually lose gas through gentler tidal interactions or by having their halos of gas siphoned away. This strangulation, or starvation, halts the inflow of fresh gas to the galaxy's disk, causing star formation to slow over time. Thus, even without immediate stripping, a galaxy in a group can gradually exhaust its fuel and redden. Environment, whether in a modest group or a giant cluster, ultimately influences whether a galaxy continues to flourish with new stars or settles into passive adulthood. For galaxies, the environment can be both nurture and executioner. It provides opportunities for interaction and growth. Yet in extreme cases, it can also cut galaxies off from the supplies that sustain their brightness. A spiral that might have lived a long star-forming life in isolation can be prematurely aged by the company it keeps in a cluster, left as a quiet shadow of its former self. In this way, the grand ecology of the universe plays out. Galaxies are not only architects of their own evolution, but also products of the environments they inhabit. Every cluster's core brims with old red galaxies that bear witness to a transformational journey, one that likely involved being stripped, quenched, and perhaps merged amid the commotion of a crowded cosmic city. Yet even as environment can strip galaxies of material, it leaves behind traces to be found. The stars that are torn from galaxies by harassment or mergers do not disappear, but linger in the cluster as a diffuse haze of intergalactic stars or in tidal streams arcing through space. In the next chapter, we will look closer at these stellar remnants, the streams, shells, and other debris that act as fossil records of past galactic meals and close encounters. When galaxies dine on smaller companions, they often leave crumbs behind in the form of stellar debris. Long after a merger or accretion event, traces of the devoured galaxy can remain drifting Victor's halo. These traces appear as ghostly streams and shell-like structures, faintly luminous against the darkness of space. They are the archaeological record of a galaxy's past meals, stellar remnants that allow astronomers to piece together an evolutionary history. By mapping these streams and shells, we effectively read the diary of past mergers written in the language of stars. Tidal streams are among the most evocative of these remnants. As a small galaxy is torn apart by a larger one, its stars are not at once. Many of them are pulled out gradually, tracing the orbit the smaller galaxy once followed. The result is a long, sinuous streamer of stars that wraps around the host galaxy. Over time, these stars descend along the path, forming a faint, gravitationally unbound stream. To a telescope, such a stream looks like a tenuous band of starlight encircling or trailing off from the main galaxy, almost like a gossamer ribbon. They can stretch for hundreds of thousands of light years, looping around the galaxy in great circles, or arcing out into intergalactic space. Our own Milky Way provides a striking example. It is currently in the process of cannibalizing several dwarf galaxies. One of them, the Sagittarius dwarf galaxy, is being gradually ripped apart, its stars pulled into a sprawling tidal stream that wraps around the Milky Way's halo. This Sagittarius stream forms a gigantic loop overhead, though it is invisible to the naked eye because its stars are so distant and sparse. Through the meticulous work of observers and the mapping power of missions like Gaia, we can trace this stars and recognize it as the remains of a once independent galaxy now merging with our own. Similarly, the Milky Way's halo contains other stellar streams, each a whisper from a past merger. One such stream associated with a dwarf galaxy that plunged through the Milky Way long ago, an event often referred to as the Gaia Enceladus or Gaia Sausage merger. This ancient collision, which occurred roughly 10 billion years ago, is thought to have been a defining event that puffed up the Milky Way's disk. The stars from that galaxy, identified by distinctive motions and chemical compositions, now suffuse our halo. They form much of the Milky Way's thick disk and inner halo populations we see today. In other giant galaxies, especially nearby Andromeda, we observe a veritable jumble of such streams. Andromeda's halo is laced with numerous faint streams and clouds of stars. Thought to be remnants of many dwarf galaxies, it has devoured over the eons. One prominent example is the giant stellar stream, an enormous sweep of stars in Andromeda's outskirts, likely originating from a single companion galaxy torn apart long ago. Each stream in Andromeda's outskirts arcs across the sky like the remnants of a shredded stellar tapestry, reflecting a history rich in mergers. By studying the positions and velocities of stars in these streams, astronomers can work backwards, reconstructing the orbits of the progenitor galaxies and when they were torn apart. It is a bit like reconstructing a crime scene. The stars are clues left scattered about, which, when analysed, reveal the story of who fell victim to Andromeda's gravity and how. Then there are the shells, another class of relic that speaks to past collisions. Shells are faint, concentric arcs, or ripple-like structures, often found in the outer regions of elliptical galaxies. They were first noted by astronomers in the 1980s, when deep images revealed subtle ripples in the halos of otherwise smooth galaxies. Sometimes shells appear on opposite sides of a galaxy as mirrored layers. Other times they form a series of nested loops encircling the galaxy. They look as though someone dropped a pebble in a galactic pond and the ripples were frozen in place. In reality, shells form when a smaller galaxy plunges nearly head-on into a larger one. The infalling galaxy's stars, moving on radial orbits, begin to pile up at the outermost reach of those orbits. Their farthest distance, the stars slow down and linger before turning back inward. This brief congestion of stars at similar radii creates shell-like overdensities, with each oscillation of the stars through the larger galaxy. Successive shells can appear, forming multiple arcs at various distances. Shells are usually very low surface brightness features, requiring deep imaging to detect. But when they are revealed, they present a beautiful and telling sight. For example, certain ellipticals, like NGC 3923, are famous for their extensive shell systems. Dozens of delicate, curved stellar filaments, nested one inside another in the galaxy's halo. These structures are essentially the remains of one or more swallowed galaxies whose stars now oscillate within the host. Each shell indicates a kind of bounce of stars, the point where the stars from the infalling galaxy reach their farthest extent before falling back inward. What do these streams and shells tell us? Collectively, these streams and shells are direct evidence that large galaxies grew by accreting many smaller ones. Every faint stream of stars in a halo testifies that the galaxy it surrounds was once less massive and built itself up by consuming others. The detailed properties of a stream, its orbital path, stellar population, and width provide clues to the mass and timing of the past accretion. A thin, coherent stream implies a relatively recent disruption of a satellite, one not yet fully dispersed. A broader diffuse stream might indicate an older event whose stars have largely mixed into the halo. Even the chemistry of the stream's stars can betray their origin, since stars born in dwarf galaxies often carry distinct chemical signatures compared to those native to the larger host. Stellar streams and shells also enrich the space around galaxies in subtle ways. Some of the stars lost from disrupted satellites become part of a diffuse halo of the larger galaxy, a sort of stellar haze that extends far beyond the main body. In clusters, streams from many different interactions can intermingle, contributing to the vast cloud of intergalactic stars that float freely between cluster galaxies. It is estimated that a significant fraction of stars in rich clusters lie outside any one galaxy, likely the cumulative result of countless tidal stripping events over time. Under the cluster's night sky, these homeless stars would form a very faint background glow, the scattered ashes of galaxies. For observers on Earth, the discovery of streams and shells has been like uncovering a hidden dimension of galaxies. What once appeared as relatively smooth, quiet outskirts now are known to contain dynamical records of violence. Each faint streak or arc of stars is a memorial of a galaxy that no longer exists in its original form. And our own night sky, could we see it from outside the Milky Way, would show similar faint pathways, pictures of the Milky Way's appetite. As we sift through these clues in galactic halos, a picture emerges of galaxying and changing by consuming smaller systems. It's a slow and ongoing process. Even now, the Milky Way and Andromeda are tugging on their satellite galaxies, seeding the next generation of stellar streams. In time, our galaxy's halo will acquire new stellar rivers from the disruption of the Magellanic Clouds. Told by streams and shells is one of continual renewal and transformation, a process that leads directly to the future of our own neighborhood. The Milky Way is not only consuming dwarfs, it is also on a collision course with a galaxy nearly its own size. In the next chapter, we turn to the unfolding drama of the local group, where the Milky Way, Andromeda, and Triangulum move toward their inevitable union. Under the quiet skies of our own planet, a faint patch of light in the constellation Andromeda hints at the grand future of our cosmic neighborhood. Patch is the Andromeda Galaxy, our Milky Way's nearest large companion. Across 0.5 million light-years of space, Andromeda approaches us inexorably. On a timescale of billions of years, the two giant spiral galaxies, Milky Way and Andromeda, are bound on a collision course. Along with the smaller Triangulum galaxy nearby, they are engaged in a slow gravitational dance that will ultimately reshape them into a single entity. At present, the Milky Way and Andromeda each reign over a retinue of dwarf satellite galaxies, and altogether they form the local group. For eons, the Milky Way has been relatively isolated, apart from gently accreting much smaller dwarfs. Andromeda, too, has grown by swallowing dwarfs, and perhaps even by a past major merger that built up its central bulge. One of Andromeda's peculiarities, the tiny elliptical galaxy M32, is suspected to be the core of a larger galaxy that Andromeda devoured long ago, a cosmic appetizer before the main course to come. Triangulum, M33, a smaller spiral, likely orbits Andromeda, perhaps having brushed by it in the past, to set its disk askew. Now these three spirals are the dominant masses of the local group, and gravity is drawing the Milky Way and Andromeda inexorably together. Though the galaxies are currently separated by a vast gulf of space, they are hurtling toward one another at a few hundred kilometers per second. In roughly 4 billion years, give or take, Andromeda will loom large in the night sky of the Milky Way. What once appears as a small nebula to us will grow over millions of years into a sprawling, majestic spiral, visible in breathtaking detail. As it nears, tug on our galaxy will begin to disturb the Milky Way's equilibrium. The outer edges of both galaxies may feel each other's presence first, perhaps warping or throwing out streams of stars well before the main event. When the Milky Way and Andromeda finally make their pass, the gravitational interaction will be titanic. Tidal forces will stretch and despiral arms. Immense strands of stars and gas will be flung out, forming pronounced tidal tails bridging the two galaxies. From Earth, if Earth still exists and had observers then, the night sky would undergo a complete metamorphosis. Instead of the familiar Milky Way, the sky would be dominated by the whirling form of Andromeda coming head-on. As the galaxies swing by each other, their mutual gravity will trigger shocks through their disks. One likely consequence of that close encounter will be a burst of new star formation. Clouds of gas in both galaxies, shaken and compressed by the meeting, will rush inward towards the galaxy's centers. There, in those galactic cores, new stars will ignite in perhaps a luminous starburst that lights up the merging galaxies, or even the ignition of a quasar if enough gas is funneled into the central supermassive black holes. Such a quasar could outshine all the galaxy's stars combined, a brilliant beacon visible across the cosmos for a time. For a few million years, the merged heart of the two galaxies might shine fiercely, pumping out light across the spectrum as the combined activity of starbirth and active nuclei is a peak. The gentle, steady glow of the Milky Way, we know, would be replaced by a stormy, radiant hub of newborn stars and energetic outflows. After this initial flyby, the two galaxies will likely separate again for a time, carrying on as deformed versions of their former selves. But they are now bound in a tightening waltz. Over the next few billion years after the first encounter, the Milky Way and Andromeda will loop around and collide again and again, each time losing orbital energy. With each successive pass, their stars intermingle more, and the distinct shapes of the galaxies further dissolve. Spiral patterns give way to huge stellar envelopes as stars are thrown into new orbits. The galaxies are effectively merging, their cores spiraling toward coalescence at the center of a growing combined system. Eventually, around 1 billion years from now, what began as two separate spirals will settle as one single galaxy. Astronomers have nicknamed the product Milkomeda, an imagined giant elliptical galaxy that will be the new home of both stellar populations. Deep in its core, the supermassive black holes that once anchored the Milky Way and Andromeda will drift together and merge as well, unleashing a burst of gravitational waves and coalescing into an even larger central black hole. Around that powerful center, the new galaxy will have a mass and scale rivaling the largest galaxies in our corner of the universe, a titan born from the union of two spirals. Around that center, the once flat disks of the Milky Way and Andromeda will likely be gone, replaced by a vast, puffed-up, spheroidal collection of stars. Many of those stars, including our Sun, by then an ancient star that has long since shed its outer layers, will find themselves in new orbits within this sprawling system, perhaps thrown farther out from the core during the upheaval. The night sky, for any worlds that might exist at that far future time, would look very different. A huge hazy ellipse of stars instead of the narrow band of a Milky Way. The merged galaxy will host a rich system of globular star clusters orbiting its core, families of both progenitors, and it will be largely devoid of gas needed to form new stars. What of Triangulum during this grand merger? The Triangulum galaxy, smaller than either the Milky Way or Andromeda, may participate in the encounter as well. One possibility is that Triangulum might crash into Andromeda slightly earlier, becoming a kind of appetizer to the main feast. If that occurs, Triangulum could be shredded in Andromeda's outskirts, perhaps creating tidal or a burst of star formation in Andromeda as a prelude to the larger collision. Stars would disperse into Andromeda's halo well before the Milky Way arrives for the main event. Alternatively, Triangulum might survive until the Milky Way-Andromeda merger is underway, then eventually be captured by the new Milkomeda galaxy. Should Triangulum persist entity through the initial stages, it might circle the newly formed giant as a lone spiral time before finally succumbing. In any case, it is likely that all three of the large local group members will coalesce into a single gravitationally bound mass. In the far future, instead of a local group of many galaxies, there may be just one enormous galaxy and a swarm of residual dwarf satellites that survive the carnage. During the merger process, many of the smaller satellite galaxies that presently orbit the Milky Way and Andromeda would either be flung into new trajectories or swallowed up. The large Magellanic Clouds, for instance, are likely to merge into the Milky Way well before the Andromeda encounter, contributing their stars and gas. Those galaxies' ongoing infall even now foreshadows the larger destiny of our galaxy. By the time the Milky Way and Andromeda have fully merged, the new galaxy will have absorbed essentially all of their retinues as well. Dozens of dwarf galaxies that once circled the two spirals will by then be cannibalized and assimilated into the single combined system. In effect, the entire local group of galaxies will coalesce into one. This future merger will not be an uncommon fate in the cosmos. Countless galaxies have undergone similar unions, Indeed, we observe examples of merging galaxies, like the antennae pair, in the present universe, and the largest elliptical galaxies in clusters appear to be built from many past mergers. Our own forthcoming collision is simply the next step in that long history of hierarchical growth. From the perspective of an outside observer in the distant future, the local group's transformation will be dramatic. Two grand spirals, with all their elegance and spiral structure, will have given way to one much larger, more amorphous galaxy, a giant elliptical glowing with the combined light of perhaps 1 trillion stars. Yet, even as this transformation takes over billions of years, it's not an apocalypse on the scale of individual star systems. The vast distances between stars mean that direct stellar collisions are extremely unlikely, even in the crowded moments of the merger. Our solar system, for example, might sail through the merger relatively unscathed, aside from being relocated in the sea and witnessing a changing stellar landscape. The real upheavals will be in the gravitational dynamics, the reshuffling of orbits, and the redistribution of gas. Some stars may even be cast out entirely, flung on hypervelocity trajectories that eject them into intergalactic space. These exiled stars would join the sparse population of lone wanderers between galaxies, expelled by the merger. Meanwhile, within the merging galaxies, gravitational interactions will scatter many stellar systems into new locales. Over time, the fuel for new stars will likely be used up or ejected, and the resulting giant galaxy will grow ever quieter and redder, its youthful star-forming days firmly behind it. Looking even further ahead, one can imagine the ultimate destiny of our new combined galaxy. In an accelerating, the local group of galaxies, having merged into one, will be marooned in an ever-expanding cosmic void. Distant galaxies, not bound to the local group, will have receded beyond the observable horizon. The great island universe formed from the Milky Way and Andromeda will stand virtually alone, a massive collection of aging stars adrift in darkness, with no other galaxies left visible in its sky. Future astronomers living in that distant time might find the cosmos a far lonelier place. With only their enormous home galaxy to study, they may lack visible evidence of an expanding universe or of other galaxies beyond their own. The grand tapestry of the cosmos that we know today would, for them, inferred only from subtle clues, or perhaps remain entirely unknown, lost beyond an unreachable horizon. For now, however, that grand future collision remains in the far distance. The Milky Way and Andromeda continue on their approach, silently drawn by gravity, while life on Earth goes on under a sky that still shows two separate galaxies. The faint blur of Andromeda in the night is a harbinger of what's to come. In the unimaginable future, the creatures, if any, under that sky will see a dramatically different vista, and their home galaxy will be a product of cosmic forces we are only beginning to understand. The story of our local group, from its past interactions to its future merger, encapsulates the entire saga of galactic evolution: growth through gravity, change through collision, and the continual renewal of the cosmos on the grandest scales. And even when the local group has become one giant galaxy, the process will not cease. The universe will continue to evolve, and new chapters in the story of galaxies will be written among the stars. In the silent depths of space, hidden forces are at work, cosmic clouds we call nebulae. Through the darkness, an invisible hand gently guides the dance of gas and dust, slowly drawing scattered particles together. This hand is gravity, a tireless sculptor working over eons, patiently coaxing structure from chaos. Even where starlight is faint and a nebula appears as a mere ghostly haze, gravity is there, quietly, but persistently molding the material of the universe. It begins with dust and gas drifting in the void. Tiny grains of dust, no larger than motes of smoke, wander through a vast expanse of hydrogen and other gases. On their own, these particles are insignificant, dark and cold, but they have a subtle power. They can cool the surrounding gas and radiating it away, allowing the gas to chill and settle. On the surfaces of these dust grains, stray atoms meet and link into molecules, releasing a small pulse of energy that the grains carry off into space. In this way, dust helps the gas cloud to collapse under its own weight, assisting gravity in its quiet labor. At first, the particles are incredibly far apart. A nebula can be more empty than even the best vacuum we might create on Earth. Yet across these light years of sparsity, gravity extends its reach. Wherever there is a slightly higher concentration of matter, its gravitational pull grows just enough to draw in even more nearby gas. Bit by bit, atom by atom, the cloud becomes denser in those favored regions. What was once an unnoticeable wisp of gas begins to gather into clumps, all guided by this unseen architecture. As the gas and dust collect, they begin to form filaments and knots within the nebula's misty form. From a distance, these look like faint threads trailing through a hazy cloud. Up close, each filament holds more particles than the emptier space around it, a rope of matter amid the diffuse background. It is as though gravity sketches the outline of a cosmic tapestry, weaving threads of denser material in the vast, dark loom of space. Dust plays its part in this tapestry too, clinging together, casting shadows that accentuate the nebula's features and adding texture to the emerging structure. Immense as these clouds are, their forms span a vast range of scales. A single nebula may stretch across dozens of light years, a cosmic tapestry so large that light itself takes centuries to cross from end to end. Yet within this immensity, gravity sculpts fine details. There are narrow filaments only a fraction of a light year wide, and compact clumps smaller still. By human standards, even these small knots could engulf entire solar systems, but compared to the whole cloud, they are mere specks of structure. From afar, we see an intricate hierarchy, great billowing swaths and delicate wisps coexisting, all shaped by the same invisible forces. Gravity is an artist of unimaginable patience. The gathering of material proceeds at a glacial pace over millions of years. In a human lifetime, or even in 1,000 lifetimes, a nebula's appearance hardly changes at all. But across eons, the gentle accrual of gas and dust transforms wisps into noticeable features. What was diffuse and formless slowly takes on discernible shape. We begin to discern gravity's footprints, curving tendrils and compact knots emerging where once there was only a tenuous haze. Pockets of gas, enriched with dust grains, become the seeds of something new, taking shape so gradually that the cloud seems almost eternal. Yet inevitably it is changing. In fact, a single vast cloud often gives rise not to one star, but to many. As the nebula condenses, it fragments into numerous dense pockets scattered throughout. Each pocket is like a tiny world unto itself, a region where gravity has gained the upper hand and is pulling matter inward more strongly than in its surroundings. In each, gas and dust roll ever closer, destined to become a newborn star. An entire community of stars is assembling in secret, each core a sibling in the same stellar nursery. In time, these many clumps will turn into a cluster of young stars, a family born together from the same cloud that once hid them all. Even as gravity pulls inward to create these seeds of stars, other forces resist and influence the process. The gas in a nebula is not perfectly still. It drifts and stirs with a restless energy. Tiny currents and eddies flow through the cloud, a gentle turbulence that counterbalances gravity's inward tug. This turbulence can tear some forming clumps apart, or prevent them from collapsing too fast. The dust within can act like an anchor in places, helping gas to cool and condense in one spot, even as nearby areas are churned by motion. This delicate balance between gravity's order and the cloud's disorder determines where each dense core can emerge and grow. At times, an outside nudge might disturb the calm and tip the balance. A distant supernova explosion might send a ripple through the nebula, or a passing star's gravity might tug at it as it goes by. These events squeeze parts of the cloud, compressing the gas just enough for gravity to seize the opportunity in that region. In those moments, what was invisible activity becomes overt. The cloud responds, a new clump suddenly collapsing more quickly, as if awakened. Like an unseen pressure shaping patterns in sand, such external pushes help gravity imprint new structures into the nebula's form. Dust, though only a tiny fraction of a nebula's mass, also leaves a noticeable signature on these cosmic designs. Those minuscule grains block and scatter starlight, creating dark ribbons and patches that snake through an otherwise glowing cloud. We often notice a nebula's dust by the shadows it draws. In photographs of nebulae, thick dust lanes appear as inky black silhouettes against luminous gas. It is the dust sculpting the view, revealing itself through the absence of light. Within those dark pockets, hidden from view, gravity may be at work even momently, assembling material away from the glare of nearby stars. Together, gravity and dust create the hidden architecture of a nebula. Gravity defines the grand blueprint, drawing vast swathes of gas into structure and gathering material into potential new worlds. Dust refines the design in detail, cooling the gas, fostering the formation of molecules, and painting shadowy forms in the nebula's glow. Neither force announces itself loudly. They remain quiet, persistent guides, shaping the cosmic cloud. Over time, their influence transforms a nebula from a diffuse haze into a landscape of dense filaments and dark veils, setting the stage for the next act in the cosmic story. Deep within those dense clumps, the long work of gravity and dust is about to bear fruit. As the material in each clump presses inward, tighter and tighter, the hidden interiors grow warmer under the increasing pressure. What was once cold, dark, and invisible begins to stir with a new energy. In the hushed darkness, the seeds prepared by these invisible architects edge toward a dramatic transformation. Soon, in the astronomical sense of the word, a spark of new light will ignite from within one of these collapsing clouds. The nebula's true purpose as a cradle of stars is about to be revealed. In the heart of a collapsing cloud, the long, quiet drama of gravity reaches its climax. Deep within one of those dense clumps, gas and dust have been falling inward for countless millennia. The pressure at the core of the clump builds as more material piles in. Bit by bit, the temperature rises in that hidden center. What was once cold and dark is now warming and glowing faintly, sheer force of its own collapse. The moment is approaching when a new star will awaken. At first, this star remains concealed in darkness. It is not yet but a hot, dense ball of gas still gathering mass. Around it, The material begins to swirl, caught in the tug of the nascent star's gravity and its rotation. The collapsing cloud cannot all fall straight inwards. It has a slight spin from its origins, and that spin causes the infalling gas to flatten into a broad disk encircling the forming star. In this whirling disk of gas and dust, countless tiny grains continue to collide and stick, forming clumps that one day might grow into planets. For now, though, the disk is an essential part of star birth, a cosmic cradle catching material as it feeds the young star at the center. Within the core, the temperature climbs higher with each passing century of collapse. Millions of particles squeeze into an ever smaller space, colliding and heating up. When the core's heat and pressure soar enough, an extraordinary change occurs. Hydrogen atoms begin to fuse together to create helium. This fusion releases a tremendous burst of energy. At that instant, the protostar becomes a real star. A new spark of starlight flickers on deep inside the cloud as the young sun ignites its nuclear furnace. It's not an explosion, but a steady burning that will last for millions or billions of years to come, marking the true birth of the star. The newborn star shines fiercely, though at first its light is smothered by the cocoon of gas and dust around it. Like a candle flame inside a foggy lantern, its glow is diffused and hidden. But the star's energy is relentless. Light and heat push outward, and the star also begins to throw off streams of charged particles known as stellar winds. Twin jets of hot gas erupt from the star's poles, blasting holes through the surrounding cloud. Where these jets collide with nebula material, they create brilliant glowing shockwaves, like cosmic arrows piercing the dark. These outflows are the young star's way of shedding excess energy and momentum. In doing so, they carve the first clear paths out of the nebula. Through these narrow channels, the newborn star's light and heat finally begin to escape into space. Gradually, the veil around the star lifts. The intense radiation from the star's surface strikes the inner walls of the cavity it has opened, causing the gas there to glow in vivid colors. The once invisible nebula now begins to shine openly by its own offspring. What was a cold, dark, collapsing cloud transforms into a radiant nebula, a stellar nursery lit from within. The remaining gas of the nebula, rich with hydrogen, oxygen, and other elements, fluoresces under the star's ultraviolet light. A shining region emerges where darkness used to reign, announcing to the universe that a star has been born here. As time goes on, the young star's brilliance and wind clear away more and more of the lingering gas and dust. In the immediate neighborhood of the star, much of the nebula's material is blown outward or heated until it disperses into space. Only the disk closer remains relatively intact, continuing to feed the star and gradually coalesce into new worlds. Farther out, the nebula's once dense clump has become a hollowed-out shell, with a bright star now visible at its center. The cradle that formed the star is being reshaped by the moon radiation, even as parts of the cloud farther away remain in shadow, still cold and waiting for their turn to collapse. In many cases, a single cloud gives birth to not just one star, but a whole community. While one protostar ignites, others in neighboring clumps are doing the same. A nebula can form dozens or hundreds of stars in relatively quick succession. Some of these newborn suns are massive and brilliant, while others are smaller and faint. Together, they light up the cloud from within like a cluster of lanterns in the mist. The result is a stellar nursery, a glowing nebula filled with infant stars, each at its own stage of development, bound by their common birthplace. Some of these stars will be much more massive and luminous than the rest, their fierce radiation dominating the nebula's glow. One of the most famous examples of such a cosmic nursery is the Orion Nebula, hanging in the sword of the constellation Orion. For countless ages, a dark, cold cloud lay in that region of space. Now it shines as a faint, ethereal glow in the night sky, the middle star of Orion's sword, visible even without a telescope on a clear night, and it reveals stunning detail in telescopes. Within the Orion Nebula, thousands of young stars and protostars are gathered. 4 of the brightest, known as the trapezium, are massive hot stars whose intense light makes the nebula glow vividly. Around many of the fainter young stars in Orion, astronomers have observed dark disks silhouetted against the nebula's brilliance. These are new planetary systems just beginning to form, the leftovers of the star formation process that will one day become planets. Our own sun was once one of these babies, born in a similar cloud billions of years ago. It likely emerged alongside a cluster of siblings in a now long dispersed nebula, sharing its birth with dozens of other stars. In a sense, all of us on Earth are children of such a nebula. For that stellar nursery set the stage for our sun and the planets that formed around it. The nebula that cradled our sun has long since vanished, blown away by stellar winds and time. But we see the story replayed in places like Orion. It is a reminder that every star, including the one that warms our world, began in the gentle embrace of a dark cloud that gave way to light. The transformation from a cold, dark clump into a radiant nursery marks the beginning of nebula's visible life as a cradle of stars. What was once a mere shadow in space becomes a luminous beacon. Yet the story does not end with the star's birth. Those newborn stars, bright and energetic, will not simply sit quietly in their nursery. They are about to drastically alter the very cloud that formed them. With powerful radiation winds, they will sculpt and shape the remaining nebula, creating some of the most breathtaking structures we can observe. Nursery, now alive with starlight, becomes the canvas for the next stage of creation as the young stars turn into artists, molding their celestial cradle into fantastic new forms. The young stars do not remain idle in their birthplace. With their arrival, they become sculptors, actively molding the cloud that once nurtured them. The first flood of intense starlight sweeps through the nebula, and with it comes a cascade of changes. Ultraviolet radiation from the hottest new stars ionizes the surrounding gas, charging it and making it glow. The nebula brightens like a cosmic dawn, its colors blooming as different atoms emit their distinctive hues. It is as if a cathedral of gas has been lit from within by 1,000 lamps. Hydrogen flushes the cloud with soft red light. Oxygen adds eerie green-blue tones. Other elements contribute wisps of purple and gold. This radiation is not gentle. It carries pressure, pushing on the gas and dust. Where the starlight strikes the walls of the cloud, it heats the gas, causing the gas to expand and rush outward. The once silent nebula now becomes a place of blistering activity. A bubble of ionized gas grows around each bright star, an expanding sphere where the gas glows and thins out as it is driven away. At the edges of these bubbles, the nebula's material piles up into bright, curving fronts, the boundaries between the star's influence and cold cloud. These glowing edges mark the advance of the stellar radiance, like a sunrise to dark landscape. In some regions, denser clumps of gas resist this onslaught. They act like cosmic rocks in a stream, sheltering the material directly behind them from the force of the radiation. As a result, the surrounding gas is eroded away, but the protected gas behind the clump survives a bit longer. This process forms elongated shapes known as pillars or elephant trunks, narrow columns of gas and dust pointing toward the source of the radiation. The famous pillars of creation in the Eagle Nebula are a prime example. Towering, dark shafts of gas left standing because their tips were dense enough to block the intense starlight, even as everything around them was stripped away. Inside those pillar tips, new stars may be forming, hidden and safe for now. Eventually, the relentless light eats through their curtains. Meanwhile, the newborn stars unleash more than just light. They also blow out fierce stellar winds, streams of high-speed particles flowing from their surfaces. These winds plow into the nebula at hundreds of kilometers per second, creating shock waves that can compress the gas. A powerful star can carve out an enormous cavity around itself with these winds, essentially clearing a space free of gas. In the process, the wind piles the displaced gas into expanding shells and bubbles. The bubble nebula is one such structure. An almost spherical shell of glowing gas, continuously inflated by the wind of a single massive star at its center. Within that bubble, the star resides in a tenuous, hot void of its own making. The bubble's edge shines where the ejected gas rams into the beyond. All of this stirring and shaping injects new turbulence into the cloud. The nebula becomes a stormy environment, a cosmic weather system driven by starlight and stellar gales. Gas swirls in eddies at the boundaries of hot and cold regions. Some of the material that was once pulsing is now caught in rapid motion, twisted into delicate filaments and wisps. The interplay of forces creates complex patterns, scalloped ridges where ionization fronts eat into the gas, knots and whirls where winds collide and intermingle, and clearings where only thin veils of gas remain. What was once a relatively uniform dark cloud transforms into a fantastical panorama of cavities, pillars, arches, and filaments. The colors of the nebula grow richer as these processes continue. Ionized emits a ruby-red glow along the edges of the cavities. Oxygen, freed from stars and shock-heated, glimmers in blue-green ribbons tracing the outlines of bubbles and shock fronts. At times, we see dark shapes moving against this bright backdrop. These are clumps of dust that have survived, being slowly and reshaped by the winds, casting ever-changing shadows. The entire nebula takes on a new appearance, one defined by the influence of its stellar inhabitants. It is as though the stars are artists, and the nebula their canvas, continually being repainted by light and wind. In this dynamic, new stories begin, even as others end. The compression of gas by shock waves can of yet more stars in some locales, as squeezed clumps collapse anew. In other places, rocks snuff out star formation by dispersing the gas too quickly. Creation and destruction play out side by side. We might witness, on the fringes of a pillar or along the edge, a small globule of gas collapsing into a nascent star precisely because a nearby star's wind compressed it. In this way, the actions of one generation of stars can sow the seeds for the next, sculpting not only the nebula's shape, but its future potential. Every nebula shaped by these forces becomes a unique spectacle. Some resemble landscapes of clouds and cliffs, with voids carved like valleys and dense regions standing like mountains against the stellar winds. Others, like the Carina Nebula, spread out in a tapestry of ridges and furrows, each ridge a wall of gas, lit brilliant by clusters of massive stars. No two nebulae are alike, yet all share the common story of being moulded by their stars. The turbulence, once a background whisper, is now a loud artist's tool, twisting clouds into braided streams and chaotic swirls that catch the starlight in unexpected ways. As we gaze upon these majestic shapes, it's humbling to remember that they are temporary. The same forces that create such beauty will eventually disperse the nebula entirely. With each passing millennium, the pillars shrink, the bubbles grow larger and leak their contents to space, and the once rich cloud thins out. The young stars, in carving out their cosmic nursery, are also effectively destroying, or rather, transforming it into a new state. Soon, only the stars themselves, and perhaps a faint remnant glow, will be left where once a great nebula stood. Yet the saga of stellar influence is far from over. The most massive of these bright young stars have short lives. In a few million years, some will reach the end of their life cycles, and will be spectacular. A titanic supernova explosion that will outshine whole galaxies for a time. When a star dies in such a dramatic fashion, it too leaves a mark on the cosmos. A new kind of nebula, vastly different in shape and origin. These explosions and their aftermaths are the ultimate sculptors, blasting star stuff into space and creating vast, ghostly clouds. The peaceful carving of nebulae by light and wind will soon be joined by this violentry. From the graceful work of living stars, we turn to the chaotic remnants of dead ones, the sprawlings that a supernova leaves behind. When a star dies in a cataclysmic blast, it leaves behind some of the most hauntingly beautiful nebulas in the universe. A massive star, having burned its fuel in a few short million years, can end its life as a supernova, a titanic explosion that for a moment outshines entire galaxies. In that instant of death, the star ejects its material into space at incredible speeds. What was once the star's core and envelope is blown outward in a brilliant, expanding shell. The darkness of space is suddenly painted with a burst of new light and debris, a violent last breath that echoes for millennia. After the initial flash fades, a new nebula begins to grow from the explosion's aftermath. An expanding shockwave races outward, ploughing into the surrounding interstellar gas. Behind it follows the star's scattered guts, hot gas enriched with heavy elements, hurled out sections. This is the birth of a supernova remnant, a sprawling, ghostly cloud that marks the spot where a star once lived. At first, it is a nearly invisible wave of energy, but as it sweeps up and heats the interstellar gas, the remnant becomes visible as a faint, glowing shell that grows larger with each passing year. Up close, a supernova remnant is a tangle of filaments, knots, and arcs. The explosion is rarely perfectly even. Some parts of the star were denser or expelled faster, and these differences show up as intricate structures in the expanding cloud. Thin tendrils of gas, glowing in reds and greens, twist and curl through the void. Each filament is like a thread in a cosmic spiderweb, outlining where shock fronts are ploughing through space. These filaments can be unimaginably long. Some stretch across dozens of light years, yet they are so thin and tenuous that they resemble wisps of smoke or gossamer threads when seen from Earth. As the gas expands, it cools, and its initial blast energy diminishes, but it remains incredibly hot and vibrant. The atoms within it, energized by the shock, shine with distinctive colors that reveal their identity. We see the telltale crimson of hydrogen, shocked by the blast, the soft green-blue of oxygen that was forged in the star's heart, and hints of deeper blues and purples from elements like sulfur and neon. In effect, a supernova remnant is a chemical treasure chest opened and spilled into space. The material flung out carries all the complex elements the star created in its lifetime: carbon, iron, calcium, and more, now mixing into the galaxy at large. Every heavy element on Earth, in our blood and bones, once flew out from such an explosion long before our sun was born. One famous example of a supernova remnant is the Crab Nebula. In the year 1054, observers in China and elsewhere noted a new star appearing suddenly in the sky, bright enough to be seen in daylight. For a time, this mysterious star outshone nearly everything in the night. That guest star was a supernova in our own galaxy, about 6,500 light-years away. Today, almost 1,000 years later, we gaze at the Crab Nebula, the expanding cloud of debris left behind. Through telescopes, it appears as an oval patch of diffuse light, filled with an intricate web of filaments. Those filaments are the shredded remains of the star, still racing outward. At the center of the Crab Nebula, pulsar, the collapsed core of the star, now a rapidly spinning neutron star, which blinks like a lighthouse and powers the nebula, making it glow in X-rays and visible light. The Crab Nebula's delicate tendrils and eerie glow stand as a time capsule of that long-ago explosion, expanding gradually into the surrounding space. Another spectacular remnant, though much older, is the Veil Nebula in the constellation Cygnus. The Veil Nebula is so large that it sprawls across an area of the sky about 36 times the size of the full moon, though it is too faint to see without a telescope. It consists of long, sinuous filaments of gas, draped in space like the tattered remains of a cosmic veil. These filaments glow with rich colors, oxygen in teal, hydrogen in red, tracing the outline of an ancient supernova blast wave that occurred thousands of years ago. Looking at the Veil Nebula, one can almost sense the motion frozen in time. The graceful, wave-like patterns reveal where the shock front rippled through the medium, leaving a shimmering footprint that slowly fades over millennia. Not all stars die with such violence. Smaller stars like our Sun will never undergo a supernova. Instead, when a Sun-like star nears the end of its life, it gently sheds its outer layers into space over tens of thousands of years. The result is a different kind of ghostly nebula, called a planetary nebula. Despite the name, these have nothing to do with planets. Early astronomers simply thought they looked round and planet-like in their telescopes. In truth, a planetary nebula is the delicate shell of gas cast off by a dying star, glowing from the ultraviolet light of the small, hot, stellar core left at the center. These nebulae often take on beautiful symmetric shapes, rings, hourglasses, or bubble-like forms. The Ring Nebula, for instance, appears as a luminous smoke ring in space, the remnants of a star's final exhalation. In the center of the Ring Nebula, one can still find the faint, white-hot ember of the star that was, quietly lighting its expanding halo. Planetary nebulae are more serene echoes of death compared to the ferocity of supernova remnants. Yet they, too, return their enriched gas back to the cosmos as their legacy. Over time, supernova remnants continue to expand and fade. After tens of thousands of years, the once brilliant disperse and blend into the general interstellar medium. What remains is no longer a distinct nebula, but the space enriched by its presence, a ghost diffused into the galaxy. Gradually, the nebula disappears, leaving only a faint memory of itself, the enriched space where it once glowed. But even in fading, these stellar ghosts influence their surroundings. The shock waves from a supernova can jolt nearby clouds of gas, compressing them and perhaps triggering new stars to form, seeding the next generation of stellar birth. And the materials, the oxygen, carbon, iron, will drift through space until one day they are gathered into new nebulae, new stars, and new planets. In this way, each stellar death echoes through time, its remnants both ending one cycle and lighting the spark of another. For centuries, humans looked up and observed faint, cloud-like patches of light in the sky without knowing what they were. They appeared as misty smudges among the stars, utterly mysterious to early astronomers. Without understanding their nature, people simply called them nebulae, the Latin word for clouds. These ghostly apparitions were noted and catalogued, but their true meaning would remain elusive for a long time. Ancient stars noticed a few smudges of light that neither shone like stars nor moved like planets. The great Persian astronomer Abd al-Sufi, for instance, recorded the diffuse glow of the Andromeda Nebula in the text, calling it the little cloud. With no tools to truly examine them, early observers could only wonder. They wove myths about the Milky Way, itself once thought a celestial cloud, but individual nebulae were often too subtle for naked eye observers and remained largely unknown curiosities in the heavens. The true age of nebula discovery began with the telescope. In 1610, soon after Galileo's first telescopic discoveries, astronomer Nicole de Peiresc turned a small telescope toward the sky and noted a strange glow around the middle star of Orion's sword. This was the first recorded sighting of the Great Orion Nebula lens. It allowed the observers to see a cloud-like form where only darkness had been before. That discovery opened the door to more of these faint celestial clouds. Over the decades that followed, other observers found additional fuzzy spots in the heavens. They noted a glowing patch in Andromeda, a faint cloud around the star cluster of the Pleiades, and many more such nebulous apparitions. These findings were intriguing. Unlike stars, patches had size and shape, but even the best telescopes of the time could not resolve them into points of light. To 17th century astronomers, they truly appeared as cloudy objects, earning the label nebulae in their writings. As telescope technology improved in the 18th century, the number of known nebulae grew. French astronomer Charles Messier was hunting comets and grew frustrated by permanent fuzzy objects that resembled comet hazes but never moved. In the 1760s and 1770s, he compiled a list of these nuisance objects so that other comet seekers would not be. This list, the Messier catalogue, became famous. It included the Orion Messier 42, the Andromeda Nebula, Messier 31, these nebulae, the Crab Nebula, Messier 1, and dozens of others. Messier's attempt to avoid confusion ended up sparking greater interest in nebulae. His catalogue provided future astronomers with a roadmap to some of the most nebulous wonders in the sky. Those faint smudges, mere obstacles in the search for comets, became prime targets for investment and awe. Nebulae were no longer mere curiosities, but objects worthy of study in their own right. Curiosity about these objects only deepened. Some astronomers speculated that nebulae might be clusters of countless distant stars, too far to distinguish individually. Others thought they might be something fundamentally different, perhaps island units beyond our Milky Way, or great clouds of primordial material. In 1785, William Herschel, using a large homemade telescope, began to survey the sky systematically. Herschel discovered hundreds of new nebulae and star clusters. With his more powerful instruments, he found that some nebulae could be myriad stars. For example, he showed that what appeared as a faint cloud in the constellation of Coma was actually a tight swarm of stars. But many other nebulae stubbornly refused to resolve, instead revealing a milky, diffuse light, no matter how he magnified them. Herschel proposed that perhaps these truly were immense clouds of luminous fluid, a cosmic material from which stars might condense. In the Orion Nebula, he thought he glimpsed star formation in progress, calling it a chaotic material of future suns slowly taking shape. It was a bold insight, the idea that nebulae could be stellar nurseries. As the 19th century dawned, nebulae continued to captivate astronomers. Some of the earlier debates about nebulae remained unresolved. What were these objects really? That question would drive new discoveries in the coming century. In Ireland, Lord Rosse built a giant telescope, 1.8 meters in diameter, the largest of its time. In 1845, with this Leviathan's town, he observed the object known as the Whirlpool Nebula and saw a swirling spiral structure. It was a stunning discovery. A spiral nebula with curving arms, a celestial whirlpool. Lord Rosse and others soon found spiral patterns in several nebulae. No one knew what to make of them. Were these swirling nebulae forming solar systems, as some speculated? Or were they separate stellar systems, as philosopher Immanuel Kant had hypothesized decades earlier in his idea of island universes? The true nature of the spiral nebulae would remain a subject of debate for many years to come. In the mid-1800s, another breakthrough tool was applied to nebulae: spectroscopy. By splitting the light from a nebula into a spectrum of colors, scientists could look for chemistries. In 1864, English astronomer Huggins turned his spectroscope toward the Orion Nebula and found something remarkable. Instead of a continuous speckled with dark lines, the signature of starlight, the spectrum showed bright emission lines, specific colors glowing nothing else. This was the unmistakable fingerprint of luminous gas. Huggins realized that the Orion Nebula was not a cluster of unresolved stars, but truly a glowing, a gigantic cloud of luminous hydrogen and other elements. In contrast, when Huggins looked at the Andromeda Nebula, he saw a faint continuous spectrum like that of stars, suggesting that Andromeda was fundamentally different from Orion. It seemed Andromeda was not a nearby gas cloud at all, but something far outside our own stellar neighborhood. The pieces of the puzzle were slowly falling into place. Certain nebulae were gaseous nurseries or remnants within our galaxy, while others, the spiral nebulae like Andromeda, were beginning to be understood as entire galaxies in their own right. By the end of the 19th century, astronomers had catalogued thousands of nebulae. The New General Catalogue, NGC, published in 1888 by John Dreyer, became the reference list for known nebulae and star clusters. Astronomers now had an extensive inventory of nebulae to explore. New technologies, such as astrophotography, were beginning to reveal these objects in greater detail. Alongside scientific catalogues, popular names also emerged. The more fanciful monikers often came from the creative impressions of observers viewing these objects through their telescopes. The Great Nebula in Orion, for instance, was sometimes described as resembling a ghostly blossom in space. The Crab Nebula received its name in 1840, when Lord Rosse's sketch of it suggested a crab's claw. In 1864, noted the striking round appearance of one nebula and dubbed it the cat's eye. As photographs improved, the silhouetted shape of a dark nebula in Orion took on the form of a horse's head, forever branding that cloud as the Horsehead Nebula. This practice of naming the unknown became a charming tradition. Astronomers likened new nebulae to whatever their shape suggested: an eagle with outstretched wings, a trifid divided into 3 lobes, a delicate rosette, a nebula shaped like the continent of North America, and so on. Each name captures a human attempt to find the familiar in these otherworldly forms. To this day, these poetic names remain in use alongside scientific designations, a testament to the wonder these objects inspire. The 20th century brought a revolution in our understanding. In the 1920s, the debate over the spiral nebulae's nature was finally settled by Edwin Hubble. Using the 100-inch telescope at Mount Observatory in California, Hubble managed to observe individual variable stars in the Andromeda Nebula. From their brightness and periodicity, he determined Andromeda was far outside our galaxy, an island universe indeed, a galaxy in its own right. The term nebula was then narrowed. No longer would we use it for whole galaxies. Nebulae came to mean clouds within our own Milky Way. Around the same time, scientists confirmed that nebulae like Orion were sites of star formation, just as Herschel had imagined. The theory of stellar evolution and the evidence from spectroscopy and photography fused into a coherent story. Stars are born from collapsing nebulae, live out their lives, and some end in explosions that create new nebulae. What were once just odd smudges of light became recognized as crucial stages in the cycle. Advances in technology allowed us to see nebulae more clearly than ever. The early 20th century saw the first detailed photographs of nebulae, revealing structures invisible to the eye. In 1880, American astronomer Henry Draper took a nearing photograph of the Orion Nebula, capturing its swirling, gaseous structure. By the mid-20th, images of nebulae graced, captivating the public with views of objects like the delicate Ring Nebula or the vast Crab Nebula. Each imprint telescopes brought new surprises. Astronomer E. Barnard, in the early 1900s, used long-exposure photographs to discover dark nebulae, not glowing clouds, but thick, light-blocking dust clouds seen in silhouette against dense star fields. He catalogued dozens of these black patches like the Pipe Nebula and the tiny round shadow of Barnard 68, revealing not entirely transparent, but sprinkled with dark clouds. These dark nebulae turned out to be the cold, dense wombs of new stars, invisible until stars in to light them up. After World War II, astronomy expanded beyond visible light. Radio telescopes hiss of cool hydrogen gas permeating space and identified radio emission from nebulae, Orion complex. Infrared telescopes peered through dust and found a wealth of hidden stars and nebulas in our galaxy. The more we looked, the more nebula we found. Huge molecular clouds that don't emit visible light but glow in infrared, and supernova remnants shining in X-rays from shock-heated gas. Our view of nebulae was now multi-wavelength and richly detailed. By the late 20th century, our view of nebulae was multi-wavelength and richly detailed. Yet nothing, however, prepared the world for the breathtaking nebula of the late 20th century. In 1995, the Hubble Space Telescope captured Pillars of Creation photo in the Eagle Nebula, towering columns of dust and gas backlit by young stars. This one image, with its clarity and drama, brought the star-forming nebulae into the public consciousness like never before. People saw, with their own eyes, the cosmic sculptures of radiation and dust that astronomers had long theorized, to deliver dazzling visions of nebulae. It revealed the intricate lace of the Crab Nebula's core, the glittering jewel-like colors of the Orion Nebula's trapezium region, and the ethereal halo of the Helix Nebula, sometimes called the Eye of God for its striking appearance. Each image not only provided scientific insight, but also deepened our sense at the cosmos. These photographs transformed nebulae from faint catalogue entries into celebrated cosmic art in the pub. As our understanding grew, so did our desire to classify and organize. Astronomers developed categories: emission nebulae, glowing clouds ionized by stars; reflection nebulae, clouds shining by reflected starlight; dark nebulae, clouds visible only by the light they block; planetary nebulae, shells from dying stars; supernova remnants, and so on. We learned that many nebulae are part of larger structures. Stellar nurseries often reside in gigantic molecular cloud complexes, and supernovas sometimes overlap or interact with neighboring clouds. We began to see nebulae not as isolated curiosities, but as integral pieces of the galaxy's ecosystem, constantly cycling matter from old stars into new. Through all these developments, the names and the sense of wonder were important. The more we discovered, the more apt those poetic names became. It's one thing to know NGC 2237 is a star-forming region in Monoceros. A photograph and instantly understand why it's called the Rosette Nebula. Its circular bloom of gas petals the world like a celestial rose. In the Horsehead Nebula, once only a small notch on a photographic plate, we now see a striking silhouette of a horse's head carved out of a curtain of gas, a testament to the power of suggestion and the interplay of light and shadow in space. Human imagination has always partnered with observation in astronomy, and nebulae are a prime example. We name what we find beautiful, and those names often carry forward the sense of awe these objects inspire. Today, armed with space telescopes and sophisticated instruments, we continue to uncover new nebulae and new details of known ones. The James Webb Space Telescope, launched in the 2020s, peered into previously hidden corners of stellar nurseries, revealing embryonic stars and intricate networks of dust in nebula like Carina and Orion. We have detected complex organic molecules in clouds and watched planetary systems take shape in the debris disks around young stars. Yet, for all we have learned, nebulae still hold secrets. They remain, in many ways, the most beautiful questions posed by nature, scenes of creation and destruction, of transition and transformation. In the journey from wondering what those faint blurs could be, to understanding their roles as stellar wombs and tombs, humanity has never lost its fascination with nebulae. The story of nebulae is intertwined with our own existence. We learned that our sun was born in such a cloud. Atoms of our bodies were forged in long ago stellar explosions and later recycled through these clouds. Every discovery about nebulae has taught us something about where we come from and where we are going. And yet, standing under the stars on a clear night, when we spot the subtle glow of the Orion Nebula or the distant smudge of Andromeda, once known simply as the Andromeda Nebula, with just our eyes, we reconnect with that original sense of mystery. We have named and catalogued the nebulae. We have unraveled many of their secrets, but the wonder they evoke is undiminished. Among the most intriguing are those nebulae that remain largely invisible to us. The quiet, cold clouds that emit little light of their own. These dark, once only inferred from the stars they hide, were among the last to be truly recognized. They remind our age of knowledge. There are cosmic nurseries lurking in darkness for curious minds and new tools to bring them to light. It is to these obscure nurseries, the silent cathedrals of gas, that we next turn our attention as our exploration of the universe's beautiful clouds continues. In the depths of space lie nebulae so quiet and lightless that only their silhouettes betray their presence. These are the dark nebulae, vast, cold clouds of gas and dust that do not glow, but instead murkily block the light of stars behind them. To the eye, they appear as voids, black patches against the bright star fields of the Milky Way. One might mistake them for holes in the heavens where no star. In truth, they are immense, invisible nurseries, holding the ingredients for countless new stars, biding their time in the darkness. Within a dark nebula, the environment is extremely cold and still. Temperatures can be just a few tens of degrees above absolute zero, cold enough that atoms cling together to form molecules. These clouds are often called molecular clouds for this reason. They are filled with molecular hydrogen, carbon monoxide, and other fragile compounds. Dust grains drift thickly through them, absorbing any starlight that tries to penetrate. If you could journey inside, you would find yourself in a nearly starless night, surrounded by an almost tangible darkness. It is a place of silence and potential, where gravity quiets clumps of matter, far from the illuminating influence of any sun. Some dark nebulae are so large they stretch across hundreds of light years, forming enormous complexes where entire clusters of stars will one day blossom. Others are smaller, self-contained globules, little pockets of night in the cosmic landscape. The coal sack, a prominent dark cloud near the Southern Cross in Earth's southern sky, is a grand example of the former. A thick, sprawling dust cloud that obscures a swath of the Milky Way. It has been known since antiquity as a dark blot against the starry band, a cosmic coal smudge awaiting the spark of starlight. In the lore of some indigenous peoples of the southern hemisphere, this dark patch was not emptiness, but part of a great cycle. The coal sack formed the head of the emu in the sky, imagined by Aboriginal Australians. In contrast, there are tiny dark like Barnard 68, which looks like a small round ink drop pasted on the backdrop of distant stars. Peering into its blackness, it reveals nothing. The starlight beyond is completely hidden by the cloud. Using infrared observations, can astronomers peek inside, revealing that even this apparently empty void harbours the seeds of stars. Even a cloud as small as this could one day collapse to form new stars, proving that no nebula is truly empty or idle. In these lightless nurseries, time moves slowly. A dark nebula can persist for millions of years, unchanged to an outside observer. Deep inside, however, the subtle drama of creation is unfolding. Dense pockets of gas gradually draw matter inward, forming what will become stars. Unlike the more famous bright nebulae, here there is no radiant display to announce the process, no colourful emission, no reflection of a nearby star's light. All is dark and seemingly inert. But in the long silence, gravity is doing its work. Molecules bump and combine on dust-grained surfaces, initiating chemical dances that influence the newborn star's environment. Layer by layer, atom by atom, these clouds prepare for the moment they will ignite into life. Sometimes, an external trigger nudges these quiet clouds into action. The shockwave of a distant supernova might ripple through a dark nebula, compressing parts of it and kick-starting the collapse of new stellar embryos. Other times, two molecular clouds might drift into one another, their gentle collision lighting a subtle spark that sets off multiple collapses. And occasionally, a dark cloud simply reaches a tipping point on its own, an imperceptible accumulation of mass that finally gives gravity the upper hand over the cloud's internal pressure. When that moment comes, what was silent and invisible begins to change. The quiet nursery starts to awaken as the deepest parts of the cloud warm up under the contraction and a faint infrared glow emanates from within. For now, though, these nebulae remain subdued. There is a profound serenity to them. Consider, hypothetically, inside one of these dark clouds. You would be enveloped in pitch-black calm, with no stars visible around you. Only the occasional distant molecule colliding, a whisper of gas moving between grains of dust. It is a cosmic night that has never known a sunrise. And yet, all around you, the raw material of stars and planets is gathered, like a great sleeping forest full of seeds waiting for spring. The darkness is not emptiness, it is fullness awaiting the right moment. When the first newborn stars in such a cloud finally ignite, the darkness will begin to lift. A tiny pinprick of light will appear where none was before, and then another, and then dozens, as the silent nursery gives birth. The once dark cloud will start to glow. Perhaps it will become an emission nebula, like Orion, announcing the arrival of its stars with a burst of colour. Perhaps the new stars will blow bubbles and carve pillars, turning the former darkness into a scene of light and shadow. The long stillness will have given way to the brilliance of a stellar nursery in full bloom. Until that day, we study these dark nebulae with patience, and with instruments that let us peer into their obscurity. The James Webb Space Telescope, for instance, can detect the faint warmth of forming stars inside cold clouds, unveiling embryos that our eyes could never see. Each discovery within a dark nebula is like finding a flicker of promise in a vast shadow. These observations reassure us that even where we see nothing, nature's grand processes are unfolding in secret. The quiet nurseries remind us that often begins quietly, in secret, without fanfare. The most dazzling stars in the galaxy each spent eons as an invisible whisper in a dark cloud before lighting up the cosmos. As we end our journey through these cosmic cathedrals of gas, from the bright pillars and glowing remnants to these silent, dark cradles, we carry with us an image of a universe always in transition. Nebulae, bright or dark, loud or quiet, are the ever-present link between the death of old stars and the birth of new ones. They ensure that the story of the cosmos continues, generation after generation. In the stillness of a dark nebula, one can sense the action of the light to come. It is as if the universe is holding its breath, waiting for the next act of creation to begin. Inevitably, that light will come. The quiet nursery will not remain quiet forever. Someday, perhaps tomorrow, or perhaps millions of years from now, the blossom into starlight, and the cycle will continue as our journey through the cosmos goes on. Depths of space. A ghostly light begins to shimmer against the darkness. A faint red glow, delicate and diffuse, where once there was only midnight emptiness. As we drift closer, the glow blossoms clouds of cosmic gas, alive with colour and energy. Here a nebula reveals itself, shining with its own ethereal light, like a lantern floating in the void. It is a sight both subtle and magnificent, one that invites us onward with its mysterious. This nebula glows not from any reflected light, but from within. At its heart, youthful stars burn fiercely, pouring out ultraviolet energy into the surrounding gas. That high-energy starlight excites the hydrogen atoms in the cloud, causing them to light up with a soft, ruby radiance. The effect is as if the very fabric of space has come alive, emitting a gentle luminescence that paints the surrounding darkness in vibrant hues. This self-made glow feels almost miraculous, a cosmic nightlight shining on its own, sustained by the power of newborn suns. It is a quiet, steady beacon that turns invisible energy into visible colour, and we find quietly marvelling at the transformation. It is as though the nebula itself is alive with light, a beacon of creation in the vast night. We find ourselves in a vast stellar nursery, a region where new stars are being born among the glowing gas. The nebula's colours swirl and blend, deep reds and pinks from hydrogen, hints of green or blue, where oxygen and other elements are energized. These colours are faint to the human eye, yet through careful observation and long exposure images, they bloom vividly, revealing the nebula's intricate structure. Filaments of illuminated gas stretch like gossamer threads, and great columns of darker dust stand outlined by the radiance behind them. The scene is complex and beautiful, tendrils of light interwoven with veils of shadow. There is structure here, and chaos too, all coexisting in a gentle cosmic dance. It is a scene of sublime chaos and ongoing creation, and we float in silent awe of its grandeur. Within this luminous cloud, star formation is underway. Dense knots of gas collapse under their own gravity, slowly gathering mass until pressure and heat ignite nuclear fire in their cores. Once a new star is born, it showers its surroundings with intense light and stellar winds. The nebula responds in kind. Gas is ionized by the star's ultraviolet rays, and the cloud glows even brighter around its stellar offspring. The young stars also carve the nebula, their radiation and winds pushing the gas into ridges and cavities. Towering pillars of gas may form where dense clumps resist erosion, silhouetted against the brilliance behind them. It's a cosmic dance of creation, light giving birth to more light, and matter organizing itself into new suns. Witnessing such events reminds us of the ceaseless creativity of the cosmos. The process is energetic, yet oddly peaceful from our vantage point. A gentle unfolding of stellar life in slow motion. One of the most famous of these glowing nodes lies in the Sword of Orion, visible on a clear winter's night as a faint hazy patch to the naked eye. Through a telescope, this patch transforms into the Orion Nebula, a sprawling emission nebula where countless baby stars nestle in rose-colored clouds. In its center, a cluster of young, hot stars, known as the trapezium, lights the nebula like a cosmic chandelier. Their fierce radiation carves cavities and shapes in the nebula's gas, sculpting towering pillars and cavernous voids. And all the while, the Orion Nebula shines with that distinctive rosy glow, proclaiming the presence of ionized hydrogen and active starbirth. This celestial nursery has fascinated sky watchers for ages, bridging the gap between myth and reality. The view of Orion's nebula is both scientific treasure and soulful inspiration, a beacon in the night that speaks to curiosity. Peering into Orion's depths, we recall the four brilliant stars of the trapezium cluster at its heart, illuminating swirls of gas and dust. This view has inspired wonder throughout the ages. In the 17th century, when astronomers first turned their telescopes to this cloud in Orion, they realized it was a star, a vast expanse of glowing gas. Such a discovery was among the first clues that the night sky held structures beyond the individual stars. Since then, the Orion Nebula has been sketched, studied, photographed endlessly, yet it never loses its magic. Even today, modern telescopes reveal new details, patterns of nebulosity, jets from newborn stars, and subtle colours that deepen our appreciation. For all our advances, this nebula continues to surprise and delight those who observe it. The Orion is often called the jewel of the winter sky, and fittingly so. It glitters softly, a constant reminder it holds grand secrets in plain sight. The more we gaze, the more the beauty of it all sinks in, calming and inspiring us under the winter stars. Not far from Orion, in our tour, Another famous shape emerges, the Horsehead Nebula. Though it is much fainter and invisible to the unaided eye, the Horsehead silhouette has become one of the most recognizable nebula images. It appears as a small dark nebula, a horse-like profile cut out from the glow of a background cloud of gas. We saw earlier how dark nebulae work, and here that knowledge meets a striking example. The hooding form stands in contrast to a field of soft red hydrogen glow behind it, creating a celestial cameo. Discovered over a century ago on long-exposure photographs, the Horsehead Nebula fascinated people with how something so distinct, a recognizable shape of an earthly creature, could exist out among the stars. It reminds us of the power of pareidolia, the human tendency to see familiar shapes in random patterns. Yet in this case, the shape is no mere illusion. It is truly there, sculpted by stellar winds and radiation into the silhouette we recognize. Over the years, the Horsehead has adorned countless books, planetarium shows, and imaginations, symbolizing the mystery lurking in the cosmic dark. As a dark form silhouetted against light, it exemplifies how the cosmos can surprise us with scenes both alien and strangely familiar. As we continue, we find ourselves face to face with towering structures made of gas and dust, perhaps the most famous nebula vista of all. These are the pillars of creation, part of the Eagle Nebula, revealed in breathtaking detail by the Hubble Space Telescope. Rising like giant stone spires in a glowing cosmic temple, these pillars are columns of cold, dark gas set against the luminous backdrop of an emission nebula. At their tips, new stars are being born, slowly eroding the material that surrounds them with intense radiation. When the Hubble photograph of this region was released in the mid-1990s, it became an instant icon, showing the world a tangible scene of star formation in action. We drift alongside these light-years tall pillars, marveling at their structure and their silent grandeur. They look almost solid from afar, like sculpted clay, yet we know they are tenuous clouds shaped by the very stars they help create. The scene is mesmerizing, a snapshot of creation caught in gentle, billowing forms. The pillars of creation captivate us, not just for their dramatic beauty, but for what they represent. The ongoing birth of stars, the cosmic cycle laid bare in a single image. It is a view that stirs something deep within, as if we are witnessing the universe contemplating beginnings. That sense of awe only deepens with the knowledge that technology used to peel back layers of this mystery. Decades after Hubble's first iconic images, newer observatories have revisited the Eagle Nebula's pillars, revealing even more. Infrared views, such as those from the James Webb Space Telescope, can pierce through some to expose stars forming inside the pillars. In every wavelength, the scene remains profound. Each advancement shows that there is always more detail, smaller tendrils of gas, fainter stars, shadows, as if the nebula has endless secret up. Perhaps it's because these structures connect to something primal in us, the concept of Genesis. The pillars of creation, as grand they are, stir feelings of wonder and origin. It's little wonder that this image adorns textbooks and inspires art. It embodies a cosmic nursery in action. In that mystery lies a quiet wonder that comforts as much as it intrigues. We feel a gentle reassurance gazing at these pillars, as if observing them brings us closer to understanding our own cosmic roots. In a different corner of the sky lies a gentler vision, often called the Eye of God. This is the Helix Nebula, a planetary nebula that appears as a huge eye-like ring in space. As we draw near, we see a turquoise halo forming a wide circle with a darker center, where the central star, now a hot white dwarf, resides. The Helix Nebula is relatively close to Earth, in cosmic terms, only a few hundred light-years away, and its apparent size in our sky is quite large. When telescopes first revealed its structure, people were struck by its uncanny resemblance to a giant eye gazing back at us. One can imagine the universe itself peering at us through this nebula, as though consciousness and cosmos are face to face. The resemblance is so striking that it has inspired a sense of being watched by the cosmos. Through a poetic lens, we feel almost observed by this stellar eye. It is a mysterious, comforting thought that perhaps the universe is aware of us, meeting our gaze with a calm, ancient eye of its own. In the helix's steady, colourful stare, there is a feeling of connection. Such impressions remind us that the shapes we see can evoke profound emotions, blurring the line between science and something that feels almost spiritual. What makes the Helix Nebula captivating beyond its shape is understanding that it is the final testament of a star like our Sun. The symmetry and calm beauty of its rings give an almost peaceful aura to what was once a dramatic stellar event. Here we have the outer layers of a star gently expanding into space, lit from within by the remaining core. The nebulas, a tranquil blue-green, complemented by faint reddish hues along the edges, create a sense of serenity. It is as though the star's violent farewell has been transmuted into a calm, visual elegy. The more we look, the more we appreciate how the universe often couches drama in beauty. To our eyes, the helix appears peaceful and ordered, belying the tremendous energies that cast it forth. In beholding it, we are both enjoying a masterpiece and reading a history of cosmic change. Even in death, a star can create something graceful, a cosmic eye that will slowly dissipate, but not before etching its image into our imagination. The emptiness inside the ring speaks of where the star's light no longer reaches, yet even that void has its own quiet message. The helix teaches us that endings can be beautiful, and that from loss can come light. It remains an obscuring wonder, an almost gentle beacon, telling us that our own sun may one day paint such a picture in the sky. Radiance, there is a sense of comforting mystery. Our journey wouldn't be complete without revisiting the Crab Nebula. Though we examined it here, the Crab Nebula is an icon not for serene beauty, but for the story it tells. To the eye, in a telescope, it is a subtle, misty patch in the constellation Taurus, requiring careful observation to discern its filaments. But historically, it has unlocked profound discoveries. Once the realization dawned that this glowing cloud was the remnant of a supernova recorded by observers in 1054, the Crab Nebula became a bridge between human history and cosmic events. For centuries, it was just a nebula of unknown origin, a curious smudge in the sky. Now we know it to be the debris of a star's explosion, a fact that forever linked a moment in human time to the life cycle of stars. It embodies the idea that the heavens are not fixed and unchanging, but dynamic and occasionally explosive. We stand in awe of the connection. Ancient people saw a new star flare up a millennium ago, and here we float beside the delicate web of gas that remains. It is a humbling reminder of how fleeting such events are on the cosmic timescale, yet how impactful on human history and science. The more we contemplate it, the more this singular nebula ties together past and present, human and cosmic. The initial cataclysm has long faded, but its memory lives on in this beautiful remnant, silently expanding in the void. The emptiness around it and the tendrils within it speak volumes about impermanence and transformation. The Crab Nebula's fame also extends to science. It was one of the first objects through which we detected things like neutron stars and understood more about energetic cosmic rays. At the nebula's heart lies a spinning neutron star, a pulsar, the tiny, incredibly dense core left after the star's demise. This pulsar flashes and breathes energy into the nebula, causing parts of it and flicker across different wavelengths. So as we float by it once more, we appreciate not just its tangled filaments, but also the narrative it carries through time. A sudden bright star that amazed and alarmed ancient sky watchers, to a modern emblem of stellar evolution studied by astronomers, the Crab Nebula ties together human history and cosmic change. It reminds us that a transient blaze of light can leave a beautiful, enduring mark on the cosmos. Even an explosion can become something quietly exquisite when viewed centuries later. There is a reflective peace in the Crab Nebula's appearance now, a peace that belies the violence that created it. The longer we gaze at its delicate structure, the more we sense a kind of resolution, a cosmic memory that has settled into a tranquil form. It is as if the universe itself remembers that great event and has arranged the remnants in a way that we can find mesmerizing rather than terrifying. The emptiness between the filaments speaks to the silence after the storm. The Crab Nebula stands as a testament to the dynamic, ever-changing nature of the sky, a gentle memorial to a titanic event. Turning our gaze southward, we encounter the majestic Carina Nebula, an expansive cloud that rivals Orion's in splendor. In its folds lies a star called Eta Carinae, one of the most massive and temperamental stars in our galaxy. In the 19th century, Eta Carinae underwent a baffling eruption that briefly luminous as a supernova, yet the star survived. This outburst expelled a glowing bipolar nebula that fans out around the star like two lobes of light, a marvel within the larger Carina Nebula. The surrounding nebula is a vast stage where numerous stars are being born in turbulent clouds of gas. Hubble's cameras once captured a view of a tall pillar in Carina, dubbed the Mystic Mountain, showing a vibrant landscape of star formation, drama to the pillars of creation. More recently, the James Webb Space Telescope unveiled the Cosmic Cliffs, an infrared vista on its edge where newborn stars carve out fantastical ridges and valleys in the gas. These images have quickly become famous in their own right, reminding us that there are countless wonders still to see. The Carina Nebula captivates us with sheer scale and the dynamic story of a gargantuan star amid a stellar nursery. It's like an epic cosmic saga frozen in a single snapshot. It is a vivid reminder that our galaxy harbors marvels on incomprehensible scales, all awaiting our gaze. The more closely we look at Carina, the more details emerge. Tiny wisps and eddies, dark globules, and glowing fronts where stars push against the gas. It is a panorama of creation, destruction, and renewal on a monumental scale. The thought that Eta Carinae may one day explode as a supernova adds a layer of anticipation to this scene. For now, the star's fury is largely spent in sculpting the nebula around it, and we are treated to the spectacle of a truly cosmic drama in progress. The enormity of this nebula, spanning hundreds of light years, challenges our comprehension and deepens our respect for the creativity of nature. Floating here, almost as if we are inside a grand cosmic cathedral, with gas pillars for columns and star clusters for shadows, a sacred space of the galaxy where the cycle of stellar life reverberates like cycle. There are other nebulae whose very names spark recognition and delight. The Rosette Nebula unfurls like the petals of a cosmic flower, its symmetric arrangement of gas and dust resembling a rose in bloom. The nebula offers a curious double-lobed shape, easily visible in small telescopes. It appears as a faint hourglass or a dumbbell, a remnant star casting off its layers. The Veil Nebula, which we touched on earlier, drapes the sky with delicate filamentary lace, the shredded remnants of an ancient supernova glimmering in faint reds and blues. Each of these carries a distinctive personality, whether its shape or colour or the story behind it, and each has earned a place in the gallery of cosmic wonders that captivate stargazers. The more we learn their names and forms, the more intimate the night sky becomes, as if we are recognizing old friends twinkling light years away. The beauty they present to us is varied, from the soft glow of a nebula rose to the thin threads of a shattered star. Yet all of it speaks the same language of awe. The universe showcases its artistry in countless ways, and we get to appreciate this grand exhibition. The more deeply we look, the more the beauty of it all sinks in, and we realize how fortunate we are to witness these natural wonders. Beyond our own galaxy lies the Tarantula Nebula, a stellar nursery of staggering scale in the neighboring Large Magellanic Cloud. It is so luminous that if it were as close to Earth as the Orion Nebula, it would cast shadows at night. The Tarantula Nebula spans hundreds of light years and contains clusters of some of the most massive and radiant stars known. It stands as a breathtaking example of star formation on a colossal scale, reminding us that there are marvels in other galaxies as awe-inspiring as those in our own. When we consider its enormity and brightness, we gain perspective on the range of cosmic environments out there. The Tarantula Nebula is a powerhouse of light and energy, a distant beacon that illuminates its entire region of space. Knowing of its existence expands our sense of wonder. Earth is not confined to our Milky Way, but flourishes throughout the universe in magnificent ways. Thinking of that immense nebula, we feel a connection to our neighbouring galaxy, as though the tarantula's brilliance reaches across space to touch our imagination. It exemplifies how nature's processes repeat on every scale, from our local stellar nurseries to far-off galactic realms. The sheer intensity of the Tarantula Nebula also hints at what our own galaxy's star-forming regions might have been like in the distant past, or could be in the future. It's a tantalizing reminder of how diverse and dynamic the cosmos is. In pondering it, we find our sense of wonder extending beyond the confines of our home galaxy, out into the wider universe. Why do these particular nebulae seize our imagination so strongly? Perhaps it's their striking appearance, or the way they hint at larger themes of creation and transformation in the universe. When the shape of a horse's head, or an eye, or pillars like mythical giants, we feel a connection between our world and the distant stars. These images remind us that the universe is not an abstract, cold expanse, but a place of tremendous creativity and beauty, with scenes that can evoke emotion and contemplation. As we reflect on them, we realize how deeply they touch our sense of curiosity and our love for patterns. The more we look, the more we find that they inspire both comfort and mystery. The familiar shapes emerging from cosmic clouds make the universe feel a little more intimate, a little less remote. It's as if nature knew we would be watching and painted these clouds in forms that our minds can recognize and appreciate. Moreover, knowing the stories behind these nebulae, the star formation in Orion, the star's demise in the Crab, the looming explosion of Eta Carinae, adds depth to the visual spectacle. They captivate us because they are both beautiful and meaningful. These nebulae act as cosmic art galleries, holding the secrets of our own origins in their forms and hues. In beholding them, we are both enjoying a masterpiece and reading a history of the cosmos. Each famous nebula we learn about becomes a chapter in the grand story of the universe, and knowing that story enriches our experience of its beauty. We recognize, then, that what captivates us is not just the light and color, but the narrative, the fact that we are witnessing creation, destruction, and rebirth on a grand scale. It humbles us and uplifts us at the same time. The interplay of knowledge and wonder makes the experience even more profound, like seeing a beautiful painting and also understanding the life of the artist who made it. With these nebulae, the universe is both the artist and the art, and we stand in quiet admiration of both. The more we learn, the more we appreciate how each glowing cloud is a bridge between science and poetry, data and dream. As our journey through these celebrated nebulae comes to a gentle pause, we carry with us a renewed sense of wonder. We have floated in the cosmic cathedrals of gas, their brilliant lights and deep shadows, their quiet births and dramatic finales. The night sky will never look the same to us, now that we recognize these nebulous forms and understand some of their stories. Yet, our exploration of the universe's grandeur is far from over. The stars seem to wink in anticipation of the next chapter of our voyage. There are always new marvels to discover and deeper insights to gain about how celestial structures shape the cosmos. With the starlight beginning to fade slightly as we prepare to move on, we drift onward, our minds open and our spirits eager for whatever cosmic wonder awaits next. The documentary of the universe continues, and we remain peaceful travelers beneath the nebula-strewn sky, heartened by the beauty we have seen and ready for the mysteries yet to unfold. Far from the city of stars, in the silent reaches between the galactic lights, immense clouds drift through darkness. They are nearly invisible in ordinary light, but they dominate the landscape of the cosmos. These are giant molecular clouds, enormous assemblies of gas and dust that span dozens or even hundreds of light years. For ages, they hang in quiet obscurity, cold and dark, harboring the raw material from which new stars will one day be born. Within one of these colossal clouds, the environment is surprisingly serene. The gas here is chilled to just a few degrees above absolute zero. Stars faint or absent, so deep inside the cloud, it is almost perfectly black to human eyes. If we could float in this darkness, we might see nothing at all around us, only the distant glimmer of far-off stars, their light muffled by thick curtains of cosmic dust. It is a realm where silence seems to reign, and time stretches out unhurried. Imagine drifting slowly through one of these cosmic clouds. Everything around you is dark and hushed. Far-off stars appear as faint, cold pinpricks of light. But nearby you see only obscuring darkness and tendrils of nebulous shadow. The silence is profound, the emptiness almost tangible. All is still, yet you sense the latent energy in the gloom, a feeling that somewhere in this quiet expanse, a star lies waiting to ignite. Yet this darkness is not empty. The cloud is made mostly of hydrogen gas, not as lone atoms, but joined in pairs as hydrogens. Mixed in are traces of other gases and delicate grains of dust forged in earlier generations of stars. Though spread thin, far thinner than the air we breathe, across these vast volumes, the total mass is enormous, amounting to tens of thousands or even millions of suns. These silent giants carry enough material to build whole clusters of stars. Drifting for millions of years, a giant cloud remains in a delicate balance. Outward pressure from the cloud's faint warmth and from stirring motions inside counteract the pull of gravity. The cloud may have formed from the merging of smaller clouds or of ancient supernovas, and now it persists as a placid, looming presence. From a distance, such a cloud reveals itself mostly by what it hides. It blocks the light of stars behind it, appearing as a dark patch or silhouette against the brighter band of the Milky Way. Such dark nebulae, for instance the Horsehead Nebula or the coal-black coal-sack cloud, are parts of larger molecular clouds. Their shapes stand out only because they blot out the starry background, like ink blots on the sky. For example, the Orion molecular cloud lies about 1,300 light-years from Earth, hidden just behind the bright Orion Nebula. This giant cloud contains enough gas and dust to form tens of thousands of stars and stretches across hundreds of light-years. Yet we perceive only the small portion of it that has already ignited. A handful of young stars illuminating a single glowing cavern of gas, creating the Orion Nebula's famous stellar nursery. The vast remainder of the Orion cloud remains cold, dark, and immense. A stellar nursery still in waiting, its thousands of potential stars not yet born. Billions of years ago, our own sun was born in a similar cloud of gas and dust. The specific nebula that cradled the has long since dispersed into the galaxy, blown away by stellar winds and time. But the evidence of that origin is all around us, in our sun itself, and in the planets that formed from the sun's surrounding disk of dust. Every star that lights up the night, every sun in the sky, began in the dark embrace of a molecular cloud. In a real sense, these clouds are the mothers of stars. Even in their quiescence, within a cloud's depths, small stirrings are always underway. Random motions of gas, slight variations in density, or the distant tidal forces of the galaxy create pockets that are a bit denser than their surroundings. Inside a giant cloud, the gas is never perfectly smooth. It's lumpy and turbulent. Threads and clumps of material swirl slowly in the gloom, as if the cloud holds secrets in its heart. Everything remains quiet to our ears. A near vacuum carries no sound we could hear. Yet gravity is gently at work, on each mote of dust and every atom of gas, coaxing them to draw closer together. For now, an internal equilibrium mostly holds, and the cloud drifts on in silence. These silent giants lies immense potential energy, patiently awaiting the right moment to be unleashed. In time, the long tranquility of a giant molecular cloud can be broken. After millions of years of subtle changes, a point is reached where part of the cloud can no longer support its own weight. Perhaps a ripple passes through, a shock wave from a distant stellar explosion, or the pressure wave of a spiral arm sweeping by. Perhaps two clouds brush against one another, sending a tremor through the gas. One way or another, a gentle tipping point arrives, and gravity seizes the opportunity it has long awaited. In that moment, though it may start imperceptibly, the collapse begins. The silent giant stirs, and the long-held promise of starlight within it is finally set in motion. Gravity's long hold on the cloud has now taken charge. At first, the change is subtle. A region of the cloud that was slightly denser and cooler than its surroundings begins to draw in material from around it. Gas and dust drift inward, slowly at first, as if an invisible hand is gathering the nebula's loose threads toward a common center. Sometimes it takes an external push to truly get things going. Imagine a powerful shock wave from a distant supernova rushing across space and slamming into the cloud's flank. In an instant, the tranquil gas is compressed and jostled. Like a muffled thunderclap in the cosmic night, the shock passes through, squeezing parts of the cloud. In its wake, some pockets that were barely balanced are suddenly overdense. These regions start to collapse, gravity now firmly overcoming any resistance. A single violent event, light years away, can thus trigger the quiet fall of gas that will form new stars. Other triggers can be more gentle, but no less effective. The Milky Way's rotating disk is full of spiral density waves, regions where stars and gas bunch together slightly, like traffic slowing on a highway. When a giant molecular cloud drifts into such a region, it feels a squeeze. Over tens of thousands of years, the cloud's passage through the spiral arm can compress it enough to kickstart gravitational collapse in multiple spots. Even the approach of another cloud, or the tidal influence of a passing star, can set parts of a nebula on the path towards starbirth. However it happens, a threshold is crossed. Somewhere in the dark interior of the cloud, gravity gains the upper hand. Once collapse has begun, the process feeds on itself. As the gas in a pocket falls inward, the region's gravity grows stronger, pulling even more material in. What started as a slow inward drift becomes a faster and faster cascade of infalling gas. From a piece of the cloud a few light years across, gas streams toward the center. Over thousands of years, a dense core, still far larger than our entire solar system, but much smaller than the original cloud fragment. The deeper it collapses, the more tightly gravity grips it, and the collapse accelerates further. It is like a snowball rolling downhill, gather momentum as it goes. If we could speed up time and watch a collapsing clump over millennia, we would see a delicate dance unfold. What once looked like a static fog would begin to swirl and gather into a concentrated mist. An ever-thickening knot would emerge at the center of that swirl, glowing faintly with the heat of its own making. All around, tendrils of gas would slowly stream inward, like rivers feeding a whirlpool, disappearing into the growing central mass. The transformation would be subtle at first, then undeniably rapid, an entire section of the cloud vanishing into a newborn protostar's embrace. Inside these collapsing regions, the hidden transformation is underway. Gas particles pick up speed as they fall, colliding more frequently at the center. This temperature at the core of the collapse. What was once an area colder than the depths of space now grows warmer. The increase is modest at first. Maybe the core climbs from just 10 degrees above absolute zero to a few tens or hundreds of degrees. But it is a sign of things to come. Pressure begins to build at the center as more gas piles in. In effect, a new object is forming, a dense, hot kernel, surrounded envelope of still falling material. This is the very early stage of a protostar, a baby star still in gestation, not yet shining with its own light. For now, this infant star-to-be is deeply shrouded. If we looked with our eyes, we would still see nothing but darkness where the collapse is happening. The dense gas and dust hide the warming core completely. Only infrared and radio waves could detect the gentle heat and motion inside. From the outside, the cloud shows few signs of the drama unfolding within. But irrevocably, gravity has lit a spark. A once quiet clump of gas is on its way to becoming a star. This process does not happen in isolation. In a giant cloud, multiple pockets may collapse at roughly the same time, especially if a widespread event like a supernova shock or the sweep of a spiral arm triggered star formation across a broad region. In effect, the cloud begins to break apart into several collapsing centers. Each will follow the same basic script: a slow start, then a faster infall, heating a hidden protostar in its core. The giant's serene facade is gone. It is now an active, chaotic place, with many dense streams of gas funneling inward. The spark of gravity has ignited numerous little fires of creation across the cloud. From here on, gravity's work continues, but other forces will also come into play. The collapsing pockets of gas are not uniform. They carry angular magnetic fields and turbulent eddies. As they contract, they will begin to fragment and flatten, developing new structures within. The scene is set for the next act of star formation. What began as a single cloud has now become a network of dense threads and clumps, each a future stellar system in the making. The collapse has truly begun in earnest, and the once silent molecular cloud is transforming into a bustling nursery of newborn stars. In the midst of this gravitational frenzy, structure emerges from chaos. The once amorphous cloud develops patterns, long, sinuous filaments of denser gas and clumps of matter along these filaments. What started as a random turbulent cloud is turning into a cosmic web, with delicate gaseous strands weaving through space. Along these strands, the collapsing material has fragmented into its and cores. These fragments are the seeds of stars, now scattered like beads on a celestial string. If we could pigeon with infrared vision, we would see the dark cloud beginning to glow in a new way. The filaments, warmed by the compression of gas, out a faintly luminous network against the colder background. They stretch for dozens of light years, yet remain slender, perhaps only a fraction of a light year thick, extraordinarily narrow relative to their length. Here and there, brighter spots punctuate the filaments. These are the dense cores, the birthplaces where protostars are coalescing. It is as if we are looking at veins of glowing ember hidden within ashes, each ember a gathering star. Forces within the cloud help craft these intricate filaments. Turbulence, the random, chaotic motion of gas, continuously stirs the cloud. Long ago, the deaths of massive stars in the vicinity may have sent gentle shockwaves through this region. In the cold, dense medium, those shockwaves travel slowly, compressing gas wherever they pass and leaving behind elongated ridges. Over time, the gas is sculpted into rope-like filaments by this interplay of turbulence and ancient echoes of star explosions. Even violence from the past thus contributes to the quiet filigree that now guides the birth of new stars. One might picture these filaments as the cloud's hidden skeleton, an intricate lacework that was invisible until gravity traced it out. They crisscross the darkness like faint highways of gas, connecting one nursery to another. In their geometry, there is a hint of order emerging from chaos, almost as if the cloud knew where to draw its threads to weave stars. It is a silent web of creation, fragile yet unyielding, waiting for the moments when each knot of gas will burst alight. These filaments are more than mere curiosities. They are fundamental to how stars form. Within a filament, gravity can work along the length, drawing material into multiple dense concentrations. A single filament might give rise to a whole chain of stars, forming in its own pocket of gas. Astronomers sometimes describe it as stars like beads on a string, as we indeed see young stars strung out along these cosmic threads. In some regions, several filaments converge toward rivers feeding a pond, and at those crossroads, especially rich clusters of stars may eventually emerge. As each fragment contracts, it may also split further into smaller pieces. Often, the collapsing core doesn't produce just one star in isolation. It may break into two or more condensations, a common center. In this way, binary star systems are born. Two sibling stars, gravitationally bound and spinning around each other from their earliest moments. Likewise, triplets or higher multiples can form, all within what was once a single cloud clump. Many of the bright stars in our night sky are actually such multiples, siblings born together in these fragmenting nurseries. Everywhere in the collapsing cloud, smaller scales mirror the larger. The giant molecular cloud has broken into clumps and filaments. Each clump can fragment further into cores. Even within some cores, substructures can arise. It's a hierarchy of creation, a cascade of ever smaller pockets within larger ones. If one could zoom out, the region that was originally a silent, uniform cloud now appears as a tangled web of filament dotted with condensations. Zooming in on any one condensation might reveal an ectostar, or a tight little nest of 2 or 3 forming stars. The complexity is astounding, yet it all stems from gravity working on the initial chaos, guided by subtle hints of order like those filaments. In cosmic terms, this entire transformation happens in the blink of an eye. Perhaps only a few 100,000 years have passed since the cloud's quiet equilibrium began to falter. In that relatively brief time, a dark and cold expanse has reorganized itself into a bustling nursery of protostars. What was once a tranquil giant has become a region of intense, if hidden, activity, forging new suns in its secret depths. During this phase, the cloud is still largely opaque in visible light. To an optical observer, there might still be little to see, aside from blackness, or a faint silhouette against the starry background. But slowly, hints of what lies inside begin to emerge. As the densest cores grow warmer and more energetic, some may start to emit faint glows, or cause the surrounding gas to fluoresce ever so softly. A delicate radiance might seep out in places where a protostar's presence is starting to make itself known. These glimmers are the heralds of the stars that will soon fully ignite. For now, though, the newborn stars remain infants swaddled in filaments and dust, quietly gathering mass. The cloud that was once a silent giant is now a labyrinth of fragments and filaments, a secret workshop where the galaxy is forging a new generation of stars. As the new stars take shape, they do so together. In the crown of the nebula, dozens, if not hundreds of stars are being born in the same neighborhood. A single cloud has given rise not to one child, but to an entire family of siblings. This gathering of young stars is what astronomers call a cluster. Within the misty cavern carved out of the gas, a cluster of newborn suns now shines, their combined light breaking through the thinning veils of their birth cloud. In these early moments, the cluster is still partially wrapped in its natal nebulous cocoon. The brightest stars cast their glow on the surrounding gas, illuminating it from within. If we were able to see it, it might look like a swarm of fireflies in a fog, each star enclosed in a gauzy. Some of the infant stars are massive and hot, blazing with a bluish-white light. Others are fainter, redder in hue, still slowly contracting and not yet as bright as they will become. Together they stud the cloud like a handful of sparkling gems embedded in cotton. We have a vivid example of such a scene in our own sky, the Orion Nebula. At the heart of that glowing cloud, in the sword of Orion, lies a tight cluster of young stars called the trapezium. These hot, brilliant stars carved out a cavity in the surrounding nebula and now light up its walls from within, revealing the stellar nursery in sharp relief. Around them, Hundreds of fainter newborn suns are scattered through the luminous haze. The splendor of the Orion Nebula is essentially a portrait of a star cluster in its infancy, a family of stars emerging together from their birth cloud. The cluster's stars are bound just shared origin. Their mutual gravity links them in a loose embrace. They move together, orbiting the cluster's of mass in a graceful, chaotic ballet. Close encounters between stars can occur in such a crowded environment, in the chaotic youth of the cluster. Most stars keep a respectful distance of trillions of kilometers, but even that is far closer than the vast isolation our sun enjoys now. If we could stand on a planet, still forming, around one of these newborn stars, the night sky would be spectacular. Dozens of brilliant stars scattered across the heavens, far brighter than any star in our current night. On a young planet, deep inside such a cluster, the heavens would be dazzling every night. Multiple suns might burn brightly in the twilight sky, and when true night fell, dozens of brilliant stars would crowd the darkness. They would cast an ethereal glow on the surface, perhaps even creating shifting shadows as they moved. In a cluster's embrace, the concept of a lonely night would fade. The sky would never truly be dark, with so many stellar companions keeping watch. Over time, the cluster emerges more clearly as the surrounding gas dissipates. The collective radiation and winds from the stars begin to blow away the remnants of the nebula that once hid them. What was an embedded cluster, hidden inside a cloud, becomes an open cluster, visible against the backdrop of space. The stars, no longer obscured by dust, can now be seen in all directions. Pillars and wisps of leftover gas still for a while, gently glowing as they reflect starlight or are ionized by it. Eventually, much of that material either falls into the stars, forms planets, or is expelled into interstellar space, leaving the young cluster in a clearer environment. Clusters come in different sizes and lifespans. Some newborn clusters may have only a few dozen members. These might disperse relatively quickly, within tens of millions of years. Others, especially those born from the largest cloud fragments, can contain thousands of stars, and their mutual gravity can hold them together longer. Still, even the grandest open clusters will gradually lose members. As the cluster orbits the galaxy, tidal forces tug at it, and interactions between the stars can fling some outward. Little by little, the cluster's stars drift away, turning a tight-knit group into scattered individuals. After hundreds of millions of years, a once rich cluster might dissolve almost entirely, its stars mingling with the general stellar population of the galaxy. During the cluster's youth, however, it is a vibrant and influential presence. Within the cluster, massive stars live fast and die young, and even before their demise they dominate the cluster's dynamics. Their intense ultraviolet light and fierce stellar winds push the surrounding gas outward, effectively halting any further star formation in their immediate vicinity. They can also affect their smaller neighbours. The radiation from an O-type star can strip away the gas disk around a nearby lower mass star, potentially disrupting the formation of planets around that star. Life in a cluster can be harsh for a fledgling solar system, as high-energy light and close encounters threaten to disperse the fragile building blocks of planets. And yet, the majority of stars in our galaxy, including possibly our own sun, are thought to have formed in clusters like this. For a time, our sun likely had many stellar siblings shining alongside it. As the cluster that bore the sun dispersed, those siblings wandered off into the Milky Way. Today, the sun travels alone, and the identities of its sister stars remain a mystery, Astronomers search for them by looking for stars with chemical fingerprints and motions similar to our Sun's, hoping to find members of our Sun's birth cluster. It is a poignant thought that many stars we see at night were once part of such close families, only to be separated over eons by the tides of the galaxy. Some clusters manage to stay together much longer. In rare cases, if a cluster is massive enough, it may remain bound for billions of years. These become the ancient globular clusters, though those form under somewhat different conditions in the early universe. But typical open clusters, the kind forming in nebulae today, are comparatively short-lived gatherings. Before they disperse, however, they offer one of the most splendid sights in the cosmos. A grouping of newborn stars, all ages of hot and cool, bright and dim, shining together, the dissipating remnants of the cloud that gave them life. Perhaps an example of a young open cluster in the modern sky is the Pleiades, the Seven Sisters. Though older than the clusters we've been envisioning, around 100 million years old, travel as a pack. They have drifted far from their birth cloud, yet faint traces of nebulous dust still surround some of them, reflecting a silvery blue light. In a telescope, the Pleiades cluster looks like a tiny dipper of stars wreathed in a delicate mist, a nostalgic remnant of the nebula from which those stars emerged. It is a glimpse of what our own stellar nursery might have become as it aged. In our forming cluster, though, we are still at the dawn of time. Only a few million years have passed since the stars ignited. Already, the brightest among them are reshaping their surroundings dramatically. The cluster shines as a beacon in the nebula, and that light is eroding and dispersing the dark cloud that once concealed it. What happens next will be both beautiful and turbulent. New stars will continue to interact with the gas around them in a complex feedback loop. The very nebula that nurtured them will be transformed by their presence. Some parts will be illuminated into great glowing regions. Other parts will be blasted away into space. The cluster will soon stand in a carved-out cavity, surrounded by the delicate shells and pillars sculpted by starlight. The era of starbirth is giving way to a new chapter, as the children begin to change the face of their mother cloud. The emergence of a cluster of youngs is not a gentle event for the parent cloud. It's a revolution. Once the stars ignite, they radically alter their surroundings. The quiet nursery becomes a scene of intense interaction between starlight and gas. There is a cosmic paradox at work. The newborn stars begin to unmake the very cloud that formed them. Yet in doing so, they also sculpt it into forms of great beauty and set the stage for new chapters of creation. The most immediate effect comes from the light of the massive stars. Their ultraviolet rays pour into the surrounding gas, energizing it. This high-energy light knocks electrons off hydrogen atoms in the cloud, ionizing the gas and causing it to glow. What was once an invisible or dark region now blossoms into a luminous nebula, an H2 region, radiating a soft crimson and pink light from the excited hydrogen. The area around the stars becomes a bubble of hot, glowing plasma. If we could see it with our own eyes up close, we would witness a sphere of diffuse rosy light expanding outward, like a sunrise diffusing through fog. This expanding bubble of ionized gas grows rapidly, pushing against the colder neutral gas beyond. A bright boundary forms, an ionization front, which is essentially the edge of the newborn star's influence. As it advances, it drives a shock into the surrounding cloud, compressing the gas ahead of it. The once uniform cloud is now divided. Inside the bubble, the gas is hot and thin. Just outside it, a dense shell of gas is swept up, and beyond that lies the remaining cold cloud. The young stars are, in effect, digging out a cavity for themselves, and piling up the material in a moving wall at the cavity's edge. If one were positioned inside the expanding bubble of an H2 region, the view would be otherworldly. The sky in every direction might glow with a soft pinkish hue, like an eternal sunset, as hydrogen gas fluoresces under stellar ultraviolet light. One would see bright young stars near the center, blazing against a luminous curtain of nebular light. Tendrils of darker, denser gas could silhouette themselves against the rosy backdrop, shaping pillars and globules that slowly shift over thousands of years. It would feel like standing in a vast cosmic cavern, its walls gently shimmering as new stars etch their story into the surrounding gas. Within this vibrant cauldron, remarkable structures take shape. Dense parts of the cloud that are not immediately evaporated by the radiation can survive as dark, elephant trunk pillars protruding into the glowing void. The famous Pillars of Creation in the Eagle Nebula are a stunning example. They are towering columns of gas and dust, several light years tall, that have been sculpted by the intense radiation and winds from nearby newborn stars. The outer layers of these pillars are being boiled away by starlight, yet inside their sheltered interiors, new stars continue to form. At the tips of the pillars, one can find embryonic stars, their presence betrayed when they occasionally pierce out as tiny jets or as glimmers on infrared images. It is a scene where creation and destruction intertwine. The pillars owe their shape to the erosive power of starlight, but within them, that same power has triggered the collapse of fresh core, forging a second generation of stars. It is an almost poetic demonstration of nature's duality. The forces that destroy the cloud also trigger new stars within it. All across the cloud, similar processes occur on various scales. A massive star might clear a spherical bubble tens of light years across. In doing so, it may sweep smaller clouds into clumps, sparking new stars along the expanding shell. In the Carina Nebula, for instance, monstrous young stars have hollowed out giant cavities, their edges lined with new star-forming knots where the gas has been compressed. Even in our Orion Nebula, the central stars have carved out a cup-like hollow in the molecular cloud. At its fringes, one finds bright ridges and globules where the next wave of star birth might be beginning, triggered by the shock of the first. Star formation can propagate outward in such a leapfrogging manner. One generation's feedback becomes the next spark. Stellar winds join the fray as well. Hot young stars do not just shine, unleash streams of charged particles, fast winds that blow in all directions from their surfaces. These winds plow into the gas like a continuous gale, further clearing out the region around the stars. When multiple massive stars are present, their winds combine into a ferocious outflow, sweep apart even hefty portions of the cloud. The winds create additional shock fronts, sometimes forming nearly spherical structures like bubbles within the nebula. One well-known example is the Bubble Nebula, a perfect glowing shell pushed outward by a central star's wind, gleaming as it plows into the ambient gas. Over a few million years, the cumulative effect of radiation and winds from the cluster's most powerful members is to disperse much of the parent cloud. The cluster, once hidden, stands revealed, and the nebula that remains is a thin veil around it, or a ring of glowing material expanding away. In time, that too will fade into the interstellar medium, leaving behind mainly the stars and perhaps some wisps of leftover dust. But while it lasts, the interplay of young stars and cloud produces some of the grandest sights in the universe. Bright nebular cavities, twisting pillars, ridges, and shells. The cathedral-like arches and chambers that gave these nebulae their nickname as the Cathedrals of gas. There is also another face to this feedback. It can inhibit further star formation by removing the raw material. Once the gas is blown away, no new stars can form in that vicinity until a new cloud drifts in, or the material cools and recombines somewhere else. In this way, the first generation of stars often brings an end to the star birth in its immediate environment, at least for a time. The cloud has effectively given all it could to the initial batch of stars, and those stars' energetic output ensures no more can easily condense nearby. For a small cloud, star formation may end after one quick burst, leaving only its newly born stars behind. In a larger cloud, star formation might continue in untouched pockets, but even there it will eventually stop under the early star's influence. Yet, feedback can also sow the seeds for new stars at the cloud's periphery. As we saw with the pillars, compression of gas can induce new collapse. This is how star formation may march outward. The cluster clears the center, but at the edges of the expanding bubble, the piled-up gas may get dense enough to collapse in spots. These will form new stars, perhaps a bit later, maybe even after the original cluster's brightest members have died out. In this sense, one generation can give birth to the next in a neighboring region, a sequential star birth that can last for many millions of years across a giant molecular cloud, until at last the entire cloud is exhausted or dispersed. And indeed, the death of the most massive stars themselves becomes the final trigger. A few million years after the cluster's birth, the heaviest stars will explode as supernovae. When a supernova detonates, it sends a blast wave racing outward at incredible speed, shock heating and sweeping up any gas it encounters. These blasts can sweep up and compress gas over enormous volumes. If any substantial molecular gas remains in the vicinity, a supernova's shock will shove it hard, potentially forcing new regions to collapse. After the initial cluster has blown away its cradle, the supernova remnants expand and collide with other clouds in the galaxy, perhaps triggering new stars far afield. It is as if the shockwaves from these dying stars carry the torch of creation outward, igniting birth in places far from the original nursery. By the end of this feedback phase, the original nebula is often unrecognizable. What started a dark, quiescent cloud has been transformed into a brilliant but short-lived display of glowing gas and dynamic shapes. Eventually, as the massive stars exhaust their fuel or blow themselves apart, the nebula's glow will fade. The remaining gas will either have formed new stars or been scattered. All that remains will be the cluster of young stars stepping into maturity under a now clear sky. The engines of creation have done their work here, and the locus of new star formation will move elsewhere. Through this turbulent interplay, we witness the full cycle of star birth in a nebula. Calm clouds condensing into stars, stars disrupting and dispersing the clouds, and in some cases prompting more star birth on a widening front. It's a self-refining process, both creative and destructive, and amid the grand-scale dramas of nebula bubbles and pillars, individual newborn stars are also leaving their own imprints on a smaller scale. In the big picture, one might miss the subtle clues that a single infant star can provide. Signs like the narrow jets of gas that young stars shoot into space. We turn now to those more intimate fireworks of star formation, the Herbig-Haro objects and related phenomena, which offer a closer look at a star's first exuberant moments. Not all the drama of star birth is on the grand scale of nebulae and clusters. Even individual infant stars put on their own small spectacles. One of the most telling signs of a newborn star is the presence of narrow, high-speed jets of gas shooting outward from its poles. In the midst of the surrounding darkness, a protostar announces itself by these faint beams of light and motion, carving through the cloud. These stellar are like a baby's first cry, an early, energetic outburst proclaiming that a new star is coming into being. Deep inside a collapsing core, as the protostar grows, it is surrounded by a spinning disk of gas and dust. The material spiraling inward doesn't all reach the star. Some of it, channeled by magnetic fields, gets redirected and hurled outward along the star's rotational axis. The result is a pair of oppositely directed jets streaming away into space at incredible speeds. Each jet is a focused stream, often only a few billion meters across, but extending for light years, and it can move at hundreds of kilometers per second. They blast out of the natal cocoon, punching holes in the dense cloud around the protostar. When these jets slam into the ambient gas of the cloud, they create brilliant, if fleeting, fireworks. The collision heats the gas to thousands of degrees, causing it to glow. We observe these impact sites as small, glowing patches in the nebula, often with a wispy, filamentary appearance. Astronomer Herbig Haro objects, after the two researchers who first studied them, but one might simply think of them as cosmic splash zones, where the newborn star's jets crash into the nursery walls. A Herbig Haro object might look like a tiny, ghostly nebula, a brief-lived blip of light marking where a jet is ploughing into its surroundings. Over years or decades, these patches can actually be seen to move and change, like bullet holes expanding as the jet continues to burrow outward. In our mind's eye, we can follow one of these jets as if riding along its beam. Near the star, the stream is hot and bright, a laser-like flow piercing the gloom. As it hurtles outward, we pass through ripples and shockwaves where the jet meets clumps of gas, creating flashes of light that fade into the emerald and ruby glow of excited atoms. Eventually, far from the star, we reach the end of the jet where it crashes into the cold cloud. There, a small, nebulous fan of light unfurls, the Herbig Haro object itself, marking the jet's terminus in a final burst of radiance. In time, that impact zone will drift further outward and dissipate, but for a moment, it stands as a signpost in the darkness, pointing back toward the hidden star that launched it. Typically, the jets come in symmetrical pairs, one jet blasting out in one direction and a second in the opposite direction. The central young star is the engine, and the jets are its exhaust, carrying away excess energy and angular momentum from the forming star. This helps the infant star continue growing. By shedding some of the spin and energy through the jets, more gas from the disk can fall onto the star. In a sense, the star is clearing its throat and stabilizing its growth by expelling some material. The process is turbulent and clumpy, so the jets often appear as a series of knots, like beads strung along an invisible line, each knot marking an episode where the protostar had a burst of ejection. Besides jets, there are other subtle clues that betray the presence of newborn stars. Sometimes, a nascent star's light escapes along the cavities carved by its outflows and illuminates surrounding dust, creating a faint reflection nebula. We see such gentle bluish glows near many protostars, lopsided patches of light where otherwise there is darkness. In other cases, sudden flares in brightness, as a young star swallows a new gulp of gas from its disk, can momentarily light up parts of the nebula. At wavelengths, certain molecules act like tiny lasers, called masers, beaming out signals from deep inside star-forming cores. Each of these suffer from a hidden star, hinting at the tumultuous growth happening within its dusty shroud. Herbig-Haro objects and related phenomena tend to be short-lived by cosmic standards. Over a few thousand years, the jet will break out of the dense birth cloud, and the supply of outflowing material will wane as the protostar settles into a more stable phase. Eventually, the dramatic jets cease, behind only the newborn star and whatever surrounding material remains. But while they last, these jets effectively bore tunnels through the cloud, like tiny drills piercing holes in a curtain. Through those cleared channels, the star's radiation can later escape more freely, helping to disperse the remaining fog around it. By observing jets and these other clues, astronomers can pinpoint sites of ongoing star formation, even when the stars themselves are not yet visible. In the Orion Nebula, for example, dozens of Herbig-Haro objects have been catalogued, each corresponding to a youthful star buried in the cloud. Each of these fleeting phenomena tells a part of the story, helping astronomers piece together how stars are born behind the veil of dust. Even as these newborn stars fling matter outward in jets, they are also gathering matter in a more organized way, much closer in. The swirling disks that flank the protostars are growing and evolving, preparing the ground for the next phase of cosmic creation. Within those disks, tiny grains of dust are beginning to stick together, and patterns are forming in the gas. The stage is set for planets to arise. The chaotic birth throes are calming, and a new kind of structure, a planetary system, is about to emerge from the remaining nebula material. That journey from dust in a disk to new worlds is the final chapter in the saga of starbirth, and it is to that we turn next. In the disk of gas and dust orbiting a new star, a quieter but no less profound transformation is underway. This flat, spinning disk is the residue of the star's formation, material that didn't fall into the star itself. At first, it is just a broad ring of fine particles and gas swirling around the newborn sun. But over time, those tiny dust grains begin to stick together. Electrostatic forces cause them to clump into fluffy aggregates. Gradually, grain by grain, the dust builds up into larger specks, then pebbles, then rocks. In the inner part of the disk, where it's warmer, metals and silicates form solid chunks. Farther out, ices can solidify, adding more material to build bigger bodies. The protoplanetary disk has become a construction site for planets. Within a few 100,000 years, some of those pebbles and rocks collide and merge, forming kilometer-sized planetesimals. In the vast spaces of the disk, these embryonic planets are like tiny islands, but their gravity begins to influence the surrounding material. They sweep up more dust and gas as they orbit, growing larger. When enough of them form, they can also collide with each other, merging into even bigger bodies. It's a chaotic, rapidly evolving scene by geological standards. Countless fragments coalescing, breaking apart, and coalescing again, slowly clearing their orbits of debris. As this process continues over a few million years, a handful of dominant protoplanets emerge. In the inner disk, where its hot and volatile gases can't easily condense, these protoplanets are made of rock and metal, the seeds of future Earth-like worlds and their rocky kin. In the cooler outer disk, beyond the frost line, ices and gases are abundant. Here, some protoplanets grow massive enough to attract and hold on to thick blankets of hydrogen and helium gas, ballooning into future gas giants like Jupiter and Saturn. Others remain as icy cores, perhaps becoming gas dwarfs or large moons. The architecture of a new planetary system is starting to take shape. It is intriguing to imagine standing on a nascent world during this epoch. The sky above might not be clear blue, but a hazy arc of glowing dust, the still forming disk seen from within, could stretch across the heavens. Instead of a moon, one might see a giant neighboring protoplanet as a bright orb embedded in the dusk of the disk. Meteors would streak by far more frequently, the leftovers of creation still crashing down. The sun, younger and more active, might rise each day shrouded by veils of remaining gas, illuminating an alien vista of half-formed landscapes under a sky still busy building worlds. Throughout this period, the young star is still settling down. Many such stars, known as T-Tauri stars, go through phases of variability and strong winds as they spin on excess energy. These stellar winds, along with radiation from the star and any nearby massive stars, begin to blow away the remaining nebula gas. The disk starts to thin out, especially the gas component. What determines the final outcome is a race. Can the protoplanets gather up their atmospheres and complete their formation before the star's winds strip the disk away? In many cases they can, resulting in fully formed planets, but in others, some potential planets might be left half-formed if the gas vanishes too soon. We have been lucky to catch glimpses of these processes in recent years. Telescopes like ALMA and the Hubble and Webb space telescopes have peered at young stars and seen the telltale patterns in their disks. In some, we observe dark gaps and concentric rings sculpting the disk's glow, likely the tracks of newborn planets clearing paths in the dust. One famous example is the star HL Tau, whose disk shows multiple rings, as though a celestial artist etched circles into the cloud. These are believed to be caused by planets in the making. In other cases, we've even directly imaged young exoplanets, faint dots near their bright stars, still glowing from the heat of formation. The once theoretical process of planet birth is now being confirmed by these remarkable observations. Even within our own cosmic neighborhood, we see evidence of this stage. The Orion Nebula, where many stars are being born, hosts not only Herbig Haro jets, but also dozens of protoplanetary disks. In photographs of that nebula, one can find small dark silhouettes against the bright background. These are proplids, or ionized protoplanetary disks, being evaporated at the edges by the intense radiation of nearby massive stars. Each of those dark ovals hides a young star at its center, and a disk that could be forming planets. The harsh environment is eroding them, but some will endure long enough for planets to take shape inside. It is a clear reminder that planet formation can be influenced by its environment. Nearby clusters or massive stars can either foster or hinder the birth of worlds. Over about 10 million years, most protoplanetary disks dissipate. The star's energetic winds and radiation blow away the remaining gas, and the dust either falls into the star, coalesces into planets, or gets ejected from the system. What's left is a newborn solar system, a star shining steadily, and a retinue of planets, large and small, circling it in the cleared space where the disk once whirled. There may still be debris, asteroid belts, comets, leftover planetesimals, but the major construction is done. The once opaque, chaotic disk has become an organized planetary system, with worlds that could, in time, harbor oceans, atmospheres, and perhaps life. Our own Earth and the Sun went through. Over 4.5 billion years ago, the Sun was once a protostar with a dusty disk. In that disk, the Earth was gradually built from microscopic dust to a massive sphere, and water-laden asteroids delivered the ingredients for oceans. When we look at nebulae and see stars with disks, we are essentially witnessing the origin story of future alien worlds, places that might one day be as rich and diverse as our own solar system. It is a humbling and wondrous realization that the night sky's nebulous glow contains, in embryo, the ingredients of new worlds and maybe new life. And so, in the cold, dark remnants of the nebula, the cycle of starbirth reaches its completion. A new star now shines where there was none before, and new planets circle it, all born from the ashes of the cloud. The once diffuse gas has condensed into suns and worlds. The cathedral of gas has fulfilled its creative purpose, at least for now. In time, the stars will continue their journey. Some of those stars, especially the massive ones, will burn through their fuel and eventually reach the end of their lives. And when they do, they may return to the cosmos, the material they once took, in a final blaze of glory. Even as we leave our stellar nursery behind, we know that elsewhere, and in the future, nebulae will bloom again from the deaths of stars, and the cosmic cycle will carry on, ever renewing the universe's most beautiful cathedrals of gas.